Imagine standing at the surface of the ocean right now, feeling nothing more than the gentle weight of air pressing down on your body from above. It is invisible, imperceptible, something you have experienced every moment of your entire life without consciously noticing. Now picture yourself descending into the abyss, sinking deeper and deeper into darkness, where every 10 meters you drop adds another full atmosphere of crushing force. At 30 meters below the surface, the pressure has quadrupled. At 100 meters, it has increased more than tenfold. And at the bottom of the Mariana Trench, nearly 7 miles beneath the waves, the pressure reaches 1,100 times what you feel right now standing on land, equivalent to having 50 jumbo jets stacked directly on top of your body, pressing down with over 8 tons of force on every single square inch of your skin. It is a force so immense that it should obliterate any living thing, reduce it to a compressed pulp, crush bones into powder and organs into paste. Yet down there, in that seemingly hostile darkness where no sunlight has penetrated for billions of years, fish swim casually through the water as if nothing extraordinary is happening whatsoever. Translucent creatures with gelatinous bodies drift past rocky outcrops. Amphipods scuttle across the sediments searching for food. Life not only exists but thrives in conditions that should be absolutely impossible. How is this possible? How do these creatures survive what would kill a human being in an instant? The answer reveals one of the most profound misunderstandings we have about the physics of our ocean, about the nature of pressure itself, and about how life can adapt to conditions that seem utterly incompatible with biology. Understanding it changes everything we thought we knew about life under pressure, about the limits of where organisms can survive, and about the fundamental relationship between physics and biology. Want to know why we have been getting it wrong all along? Why our intuitions about pressure are completely backwards, and what this means for the future of ocean exploration? Keep watching, because what you are about to discover will transform the way you think about the deep sea forever. The Titan submersible disaster of June 2023 brought the absolute terror of deep sea pressure into sharp, horrifying focus for millions of people around the world. 5 human beings descended toward the Titanic wreck site, 12,400 feet below the surface of the North Atlantic, when their vessel catastrophically imploded somewhere during the descent. The implosion was so violent, so instantaneous, so utterly devastating that the passengers aboard almost certainly never knew what happened to them. In less than a millisecond, faster than the human nervous system can even register pain signals, the walls of their cylindrical hull buckled inward as thousands upon thousands of tons of force per square inch overwhelmed the structural integrity of the composite material. The pressure at that depth, approximately 375 atmospheres, created a crushing force equivalent to 5,500 pounds, pressing relentlessly on every single square inch of exposed surface. To put that incomprehensible number in perspective that our land-adapted brains can actually grasp, imagine a great white shark, one of nature's most powerful predators, clamping its massive jaws down on your entire body simultaneously from every direction at once, except the bite force would actually be significantly greater than even that terrifying image suggests. This is precisely what happens when human engineering meets the raw, unforgiving power of hydrostatic pressure, deep beneath the waves, when we venture boldly into an environment where the sheer weight of water stacked above us becomes an invisible enemy we can barely comprehend with our surface-dwelling intuitions. The vessel simply ceased to exist as a vessel in that fraction of a second, transformed from a functional submarine into a chaotic mass of compressed debris and seawater, rushing inward to fill the void where 5 people had been sitting moments before. But here is precisely where our typical understanding stops dead in its tracks, where the explanations we have been given throughout our lives, in schools and documentaries and casual conversation, begin to fundamentally mislead us about what is actually happening. We think of pressure as something that crushes objects flat, that squashes things down, that flattens and compacts and pulverizes. We imagine it instinctively as a force pressing downward from above, like the weight of those 50 jumbo jets we mentioned, like gravity pulling everything toward the center of the Earth. And this mental model, while not entirely wrong in every aspect, catastrophically misses the fundamental nature of what pressure actually is at a physical level and how it actually works in the real world of fluid mechanics. When we talk seriously about pressure in the deep ocean, we are really discussing one very specific type of pressure that physicists and engineers call hydrostatic pressure. The word hydrostatic itself breaks down beautifully and instructively if you know even a little bit of Greek, hydro meaning water and static meaning at rest or not moving. This is the pressure exerted specifically by a fluid that is not in motion, pressure that exists purely and entirely because of gravity relentlessly pulling downward on the tremendous mass of water stacked above any given point in the ocean column. At sea level, standing on a beach or a dock or the deck of a ship, we experience exactly 1 atmosphere of pressure, which equals approximately 14.7 pounds per square inch when measured in those familiar imperial units. This pressure value represents the cumulative weight of the entire column of air extending vertically from the Earth's surface all the way up to the edge of space itself, perhaps 60 or 70 miles straight up, all of that air pressing down on us constantly. We do not consciously feel this pressure under normal circumstances because our bodies have evolved over millions and millions of years to be perfectly adapted to it, because the fluids and gases inside our bodies push outward with exactly the same force in response, creating a perfect equilibrium between internal and external pressure that our nervous system simply treats as the baseline normal state. But the very moment we enter the ocean and begin to descend beneath the surface, something fundamental changes in the pressure equation. Water, being a liquid rather than a gas, is approximately 800 times more dense than air at sea level under standard conditions. This extraordinary difference in density means that a column of seawater only 10 meters tall, roughly 33 feet, exerts exactly the same amount of pressure on objects at its base as the entire atmosphere stacked above us from sea level to space. Think about that stunning fact for a moment. Just 33 feet of water creates as much pressure as 60 miles of air. For every additional 10 meters you descend into the ocean, you add another complete full atmosphere of pressure to the total load. At 30 meters depth, a common recreational diving limit for many certified sport divers, you're experiencing a total of 4 atmospheres of pressure. 1 atmosphere from the air column above the water surface, and 3 additional atmospheres from the 30 meters of water itself. At 100 meters down, well into technical diving territory, where only specially trained divers with exotic gas mixtures dare to go, you are experiencing 11 atmospheres of total pressure. At the average depth of the world's oceans, approximately 3,800 meters below the surface, the pressure reaches an almost incomprehensible 381 atmospheres. And at the deepest point on Earth that we know of, Challenger Deep in the Mariana Trench at nearly 11,000 meters down, the pressure hits approximately 1,100 atmospheres, a number so large that it becomes essentially meaningless to our everyday experience. These numbers are absolutely staggering when you write them down and contemplate what they represent, but they tell only a small part of the complete story about what is actually happening in the deep ocean. The real revolution in understanding, the genuine paradigm shift that changes everything, comes when we truly grasp at an intuitive level what pressure actually does to objects and organisms, and what it emphatically does not do, contrary to our surface-dwelling expectations. When most people hear that deep-sea pressure can reach thousands and thousands of pounds per square inch, their minds immediately conjure an image of being compressed like a victim in a trash compactor, flattened into a grotesque pancake by an overwhelming downward force acting from above. This disturbing mental image is deeply, profoundly ingrained in our popular culture, constantly reinforced by movies and television shows and cartoons, where characters get comically or tragically squished flat under heavy falling objects or hydraulic presses. But this mental model, as vivid and intuitive as it feels, fundamentally and completely misrepresents the actual nature of hydrostatic pressure in a fluid. The critical misunderstanding, the central error in our thinking, lies in the concept of directionality and how forces behave in fluids versus solids. We think of pressure as pushing downward because our entire terrestrial existence teaches us to think of weight as pushing down toward the ground. When you carefully place a heavy textbook on a table, the book pushes straight downward with a force equal to its mass times gravitational acceleration, and the table pushes straight upward with an equal and opposite force to resist it and prevent collapse. Forces, as we learn them in basic physics classes, have magnitude and direction. They are vector quantities. But pressure in a static fluid does not work this way at all. Pressure in a fluid at rest pushes equally in absolutely all directions simultaneously, with exactly the same magnitude in every conceivable direction at any given point. This omnidirectional nature of fluid pressure is not some exotic property that appears mysteriously only in special circumstances or unusual conditions. This is absolutely fundamental to how all fluids behave at equilibrium. At any specific point in a static fluid, whether that fluid is air or water or oil or liquid nitrogen, the pressure pushes upward with exactly the same force magnitude that it pushes downward. It pushes leftward with precisely the same force that it pushes rightward. It pushes forward and backward and at every conceivable angle in between, all with perfectly equal magnitude at that point. This is such a counterintuitive concept for most people that it bears repeating and examining from multiple angles. If you could somehow place an incredibly sensitive pressure sensor in the middle of the ocean at some arbitrary depth and rotate it through all possible orientations, measuring pressure in every direction, you would register absolutely identical readings no matter which way you oriented the sensor. North, south, east, west, up, down, diagonal, every direction gives you the same pressure value at that location. This surprising fact is a direct consequence of how fluids respond to forces and has profound implications for everything from submarine design to understanding how fish survive at depth. This omnidirectional characteristic of pressure is formalized in what physicists call Pascal's principle, named after the brilliant French mathematician and physicist Blaise Pascal, who carefully investigated and formalized these ideas back in the 17th century. Pascal's principle states that pressure applied to any point in a confined, incompressible fluid is transmitted completely undiminished in all directions throughout that entire fluid. More fundamentally, for our purposes, it tells us with mathematical precision that at any specific point in a fluid at rest under equilibrium conditions, the pressure has exactly the same magnitude in every possible direction you could measure. The physical reason this must be true comes down to the definition of a fluid and how fluids differ from solids at the molecular level. Fluids, unlike rigid solids, fundamentally cannot sustain what engineers call shear stress when they are at rest in equilibrium. Shear stress is a force that acts parallel to a surface rather than perpendicular to it, like dragging your hand across a table versus pushing straight down on it. If the pressure at some point in a static fluid were greater in one direction than in another direction, creating a pressure differential that would create a shear stress in the fluid. And a shear stress in a static fluid would immediately cause that fluid to flow from the region of higher pressure toward the region of lower pressure, continuing to flow until the pressure differential was completely eliminated and equilibrium was restored throughout. The fluid would not remain static. The very definition of what makes a fluid static, what allows us to call it a fluid at rest, requires that pressure be absolutely equal in all directions at every point. Any deviation from this equality would immediately set the fluid in motion. This is why fish swimming at great depth are not pushed downward toward the ocean floor by pressure. The pressure pushes on them equally from above and below and from all sides simultaneously. There is no net force in any particular direction, due to pressure alone at any given point. The fish float in equilibrium, suspended in a medium that squeezes them uniformly from every conceivable angle, with thousands of pounds per square inch, but with no directionality to that force. Now we can finally start to see clearly why the crushing mental model that dominates popular understanding is so profoundly misleading, and why it causes such confusion about deep-sea life. When something is crushed in the way we typically imagine crushing, it experiences asymmetric force application. A trash compactor works by applying massive force from one direction, typically from above with a descending hydraulic plate, while the bottom of the compactor provides rigid resistance preventing downward motion. The unfortunate object trapped between these two opposing forces gets compressed along one primary axis, squeezed flat as the distance between top and bottom decreases. But in the deep ocean, there is no such asymmetry whatsoever in the pressure field. The pressure at any point pushes with equal magnitude in all directions. It is a scalar field, not a vector field. So why then do objects visibly get compressed when taken to great depths in the ocean? Why do styrofoam cups that are attached to deep diving submersibles and remotely operated vehicles come back to the surface, shrunken to a tiny fraction of their original size, like bizarre miniature souvenirs? Why did the Titan submersible implode so violently at depth? The answer to these questions lies not in the direction of pressure, which as we have established is omnidirectional and therefore directionless, but rather in the physical response of different materials to omnidirectional compression, and crucially in the presence or absence of internal pressure within an object to counteract and balance the external pressure surrounding it. Let us think carefully and systematically about what happens to an air-filled styrofoam cup when it gets attached to a deep-diving vehicle and descends to great depth in the ocean. Styrofoam, that lightweight white material used for coffee cups and packing materials, is made of polystyrene polymer that has been expanded and puffed full of air during the manufacturing process, creating a cellular structure that is perhaps 95% air by volume and only 5% solid polystyrene. The cup contains countless thousands of tiny individual air bubbles trapped within the solid polystyrene matrix. Each of these microscopic bubbles is essentially a miniature pressure vessel in its own right, and at the ocean surface under standard atmospheric conditions, they each contain air at approximately 1 atmosphere of internal pressure. As the cup begins its descent into the depths attached to the submersible, the external pressure acting on the cup from all sides increases steadily and predictably with depth. At 100 meters depth, roughly 330 feet down, the external pressure has risen to 11 atmospheres. Those tiny air bubbles inside the foam, each being pressed on uniformly from all sides by the surrounding water pressure transmitted through the polystyrene matrix, begin to compress in volume according to a fundamental gas law that every chemistry student encounters called Boyle's law. Boyle's law states that for a fixed quantity of gas at constant temperature, pressure, and volume are inversely related by a simple mathematical relationship. If you double the external pressure acting on a gas, you halve its volume. If you triple the pressure, the volume drops to 1/3 of its original value. At 11 atmospheres of external pressure, those microscopic air bubbles trapped in the styrofoam have therefore shrunk down to roughly 1/11 of their original volume at the surface. The polystyrene matrix itself, being a solid polymer rather than a gas, is virtually incompressible and does not change its volume significantly even under enormous pressure. But as the air bubbles within that matrix shrink dramatically, the entire structure collapses inward. The styrofoam cup becomes dramatically smaller in all 3 dimensions as the gas volume disappears, yet the shape and surface features remain recognizable because the collapse happens uniformly from all sides. The cup's total mass does not change at all. Every molecule of polystyrene is still present, but its volume decreases enormously as the compressible air is squeezed down to almost nothing. When the cup is brought back to the surface and the external pressure returns to 1 atmosphere, the air has already leaked out through the compressed polystyrene matrix during ascent, and the cup remains permanently shrunken because the foam's cellular structure has been irreversibly deformed and compressed. The key insight that we must absolutely understand from this example is that compression happens not because pressure pushes down from above, which we now know is a misconception, but because there exists a pressure differential between the inside and outside of the object. High pressure outside, low pressure inside. The gas trapped inside the foam bubbles cannot generate enough outward pressure to balance and resist the inward pressure from the surrounding water being transmitted through the foam structure, so the structure collapses inward from all directions until a new equilibrium is reached. The exact same principle, writ large and with catastrophic consequences, explains why the Titan submersible imploded at depth. The hull of the submersible enclosed a pressurized habitable space filled with breathable air at approximately 1 atmosphere of pressure, the comfortable normal pressure that the 5 passengers inside needed to breathe and survive. But outside that hull, at the tremendous depth where the structural failure occurred, the water pressure was hundreds of times greater than the internal air pressure. The hull structure, made of carbon fiber composite material and titanium, had to continuously resist this enormous pressure differential, acting as a barrier keeping the relatively low pressure air inside completely separated from the extremely high pressure water outside. When the hull's structural integrity finally failed at what investigators believe was a weak point in the composite material, or a joint between materials, probably after being weakened by repeated compression and decompression cycles on previous dives, the pressure differential drove an explosively rapid collapse. Water rushed inward with incredible violence as the much higher external pressure sought to equalize with the lower internal pressure, something fluids always attempt to do when given any pathway. The implosion was not fundamentally caused by weight pushing down from above, Though weight and gravity certainly create the pressure, it was caused by pressure pushing inward uniformly from absolutely all directions simultaneously through a catastrophic breach in the pressure hull. This is what engineers and physicists call a rapid pressure equalization event, not a crushing in the traditional directional sense that most people imagine. The distinction between these concepts matters enormously, far more than mere semantics, when we attempt to understand what happens to objects and organisms in the deep-sea environment. Consider now with clear eyes what would happen to an unprotected human body if it was suddenly exposed to deep ocean pressure without any protective equipment like a pressure suit or submarine hull. The popular science fiction image, the one burned into our collective imagination by countless movies, involves the human body being crushed completely flat, bones shattered into fragments, internal organs pulverized into an unrecognizable pulp, the person reduced to a flattened disk of biological matter. While the reality of sudden exposure to deep sea pressure would certainly be instantly fatal and utterly horrific beyond description, the actual physical mechanism of death is considerably more nuanced than simple flattening and reveals much about pressure. The human body contains several air-filled spaces and cavities: the lungs with their delicate alveolar sacs, the sinus cavities in the skull, the middle ear cavities behind the eardrums, even small amounts of gas naturally present in the intestines from digestion. At the surface, under normal atmospheric pressure, these spaces are all filled with air at 1 atmosphere. If a human body was suddenly transported by some impossible means to great depth, say 3,000 meters where pressure exceeds 300 atmospheres, the external pressure would immediately attempt to compress these air-filled spaces with tremendous force from all directions. The lungs would undergo catastrophic collapse as the air inside them compressed to a tiny fraction of its original volume following Boyle's law. The chest cavity would be forcefully contracted inward as water pressure, transmitted efficiently through the body's soft tissues, pressed inward on the collapsed lungs from all sides simultaneously. The delicate alveoli would be crushed beyond recognition. The sinus cavities in the skull would face similar violent compression, with bones potentially fracturing under the stress. The middle ear spaces would implode inward, rupturing the eardrums instantly. In practical reality, water would be forced into all these cavities almost instantaneously, rushing in to fill the space that the compressed air no longer occupied, causing massive internal hemorrhaging and tissue destruction. This process, this injury pattern caused by unequal pressure between inside and outside of body cavities, is what dive medicine specialists call barotrauma, physical injury caused specifically by pressure differences rather than by pressure itself. But here is the critical point that reveals the true nature of pressure. The solid and liquid parts of the human body, which together make up the vast overwhelming majority of our total mass and volume, would not be crushed at all in any meaningful sense. Solids and liquids are incompressible, or at least, they are so nearly incompressible that the difference is negligible for our purposes. Unlike gases, whose molecules are far apart with vast empty space between them, the molecules in liquids and solids are already packed quite close together, and their volume does not change significantly even under the most enormous pressures that exist in Earth's oceans. Your blood, being primarily water, would not compress. Your muscles, being roughly 70% water by mass, would not compress. Your bones, being solid mineral and protein matrix, would not compress. Your brain, your liver, your heart, all the dense solid and liquid tissues would remain essentially unchanged in volume even at crushing depth. Only the air spaces, only the compressible gas-filled cavities would collapse catastrophically. The body would not be flattened into a pancake, it would be drowned and hemorrhaged and destroyed by barotrauma to the air cavities, but the fundamental body structure would remain recognizable if horrifically damaged. This distinction illuminates everything about how pressure works and why deep-sea creatures can survive what would kill us. The incompressibility of liquids is another absolutely key concept that we frequently misunderstand in everyday conversation and popular science. We casually hear water described as incompressible, and we mentally file that away as meaning it cannot be compressed at all under any circumstances whatsoever, that it is absolutely rigid. This is not quite accurate, not quite the full picture. Water is nearly incompressible, but it definitely does compress slightly, measurably, under extreme pressure conditions. At the bottom of the Mariana Trench, where pressure approaches 1,100 atmospheres, water is compressed by approximately 4.5%, compared to its volume at the surface. On the scale of the entire ocean, this represents an absolutely staggering amount of total compression, enough that if the ocean floor suddenly dropped deeper by some geological catastrophe and pressure increased everywhere, global sea level would noticeably drop as the water compressed into a smaller total volume. 4.5% might not sound particularly impressive when stated as a percentage, but it represents an enormous amount of force acting on the water's molecular structure at the atomic level. The fundamental reason that water resists compression so effectively compared to gases is rooted in how tightly packed water molecules already are in the liquid state under normal conditions. In a gas like air, the individual molecules are separated by distances that are many times larger than the molecules themselves. There is genuinely lots of empty space, or more accurately, space occupied only by the kinetic energy of molecular motion between the molecules. Compressing a gas initially involves simply pushing those widely separated molecules closer together, reducing the empty space between them, which is relatively easy because the molecules do not strongly interact at those distances. But in a liquid like water, the molecules are already nearly as close together as they can possibly get based on the size of the molecules themselves and the strength of intermolecular forces. They're held at a certain average distance by a careful balance of attractive forces, primarily hydrogen bonding between the slightly positive hydrogen atoms of one molecule and the slightly negative oxygen atom of another molecule, and repulsive forces that arise when electron clouds of different molecules try to overlap and occupy the same space. To compress the liquid further beyond its natural liquid state density, you must overcome these carefully balanced forces and push the molecules even closer together than they naturally prefer to be at that temperature, literally forcing electron clouds to overlap more and interact more strongly through quantum mechanical repulsion, which requires truly enormous external pressure to accomplish. This near incompressibility property of water and other liquids explains perfectly why the non-air portions of a human body would not be crushed at depth. Your blood, being liquid water with dissolved salts, proteins and cells, would not compress significantly even at thousands of atmospheres. Your muscles, being roughly 70% water by mass permeated with protein fibers and cellular structures, would not compress in any meaningful way. Your bones, being a solid mineralized structure of calcium phosphate crystals and protein matrix, would not compress appreciably. Your brain tissue, your liver, your heart, all the dense solid and liquid tissues would remain essentially unchanged in volume, even at the crushing pressures found at the bottom of the deepest ocean trenches. Only the air spaces within your body would violently and catastrophically collapse under external pressure, and even those would not be crushed in the sense of being physically destroyed or pulverized. They would simply be filled with water forced inward by pressure differential, or the gas inside would condense and compress to a much smaller volume, as the air molecules were forced closer together, following the ideal gas law until equilibrium was reached. The behavior of gases under pressure follows mathematical laws discovered centuries ago but still perfectly accurate today. Boyle's law, named after the 17th century scientist Robert Boyle, who first formulated it, states that for a fixed quantity of gas at constant temperature, the product of pressure and volume remains constant. Mathematically, P times Vs equals a constant value. This means if you double the pressure on a gas, its volume halves. Triple the pressure, and volume drops to 1/3. This inverse relationship explains why gas-filled spaces compress so dramatically at depth, while liquid and solid materials barely change. The air in your lungs at the surface occupies perhaps 5 or 6 litres of volume at 1 atmosphere pressure. At 10 metres depth, where pressure is 2 atmospheres, that same quantity of air would occupy only 2.5 to 3 litres if your lungs could maintain their structure. At 100 metres and 11 atmospheres, it would compress to less than half a litre, a nearly complete collapse. This is why diving mammals must either surface frequently to breathe like dolphins and seals do, or must have collapsible lungs and oxygen storage in blood like deep-diving whales, or must eliminate lungs entirely and switch to gills for extracting dissolved oxygen from water like fish have done. The relationship between pressure, volume and temperature for gases is more completely described by the ideal gas law, which combines Boyle's observations with those of Jacques Charles, who studied how gas volume changes with temperature, and Joseph Gay-Lussac, who studied pressure-temperature relationships. The ideal gas law states that pressure times volume equals the number of gas molecules times a constant times absolute temperature, written as PV equals nRT, where N is moles of gas, R is the universal gas constant, and T is temperature in Kelvin. This fundamental equation governs gas behavior throughout the universe and is essential for understanding everything from Earth's atmosphere to the interiors of stars to the behavior of breathing gases in scuba diving. Deep diving physiologists use this equation constantly to calculate how breathing gas mixtures will behave at depth, how much oxygen and nitrogen will dissolve in blood at various pressures, how quickly gases will come out of solution during ascent. The mathematics of gas behavior under pressure is both elegant in its simplicity and profound in its implications for life and technology. But we should return our focus specifically to the biological implications of pressure and examine in more detail some specific pressure adaptations that evolution has produced in deep-sea organisms beyond the examples we have already discussed. The diversity of solutions is truly remarkable. Consider the protein structure modifications found in deep-sea fish. Researchers comparing protein sequences between shallow water and deep water-related fish species have found consistent patterns of amino acid substitutions. Deep-sea versions of the same protein often have more charged amino acids, particularly more arginine and lysine residues, which carry positive charges, and these charged residues are often positioned where they can form salt bridges, electrostatic attractions between oppositely charged amino acids that help stabilize protein structure. Salt bridges are relatively insensitive to pressure compared to other weak interactions like hydrogen bonds that can be disrupted by compression, so proteins relying more on salt bridges maintain their structure better under high pressure. Deep-sea proteins also tend to have fewer hydrophobic amino acids in their interiors and more polar or charged residues, which counterintuitively makes the protein slightly less stable at surface pressure, but more stable at high pressure. This is a beautiful example of evolutionary trade-offs. A protein cannot be optimized for both surface and deep-sea conditions simultaneously, so deep-sea specialists have sacrificed some surface stability to gain pressure resistance. If you could bring a deep-sea fish to the surface and keep it alive, its enzymes would actually work less efficiently at low pressure than they do at the crushing pressures of its natural habitat. The fish is biochemically adapted specifically for high-pressure environment. Another fascinating adaptation involves the amino acid composition of collagen, the structural protein that forms connective tissue, skin, blood vessel walls, and provides tensile strength throughout the body. Collagen from deep-sea fish has been found to have unusual amino acid compositions compared to surface fish collagen. Specifically, deep-sea collagen often has lower amounts of the amino acid proline and higher amounts of other amino acids that allow the collagen triple helix structure to be slightly more flexible and less rigid. This might seem backwards since you would expect deep-sea organisms to need stronger, more rigid structures to resist pressure. But remember that pressure is omnidirectional and creates no net force requiring resistance. What deep-sea collagen apparently needs is flexibility to accommodate the slight compression of tissues under pressure without tearing or failing. Rigid, inflexible collagen might crack or fracture under the slight tissue deformation that occurs at extreme pressure, while more flexible collagen can bend and accommodate the deformation without damage. Again, we see evolution finding non-obvious solutions through millions of years of trial and error, natural selection favoring whatever works regardless of whether it matches our engineering intuitions. The study of deep-sea pressure adaptations has also revealed some organisms that use entirely different strategies we have not yet discussed. Some deep-sea microorganisms produce specialized lipids called tetraether which are completely unlike the standard ester lipids found in most cell membranes. Tetraether lipids have two hydrophobic tails per molecule that span entirely across the membrane bilayer and connect to hydrophilic head groups on both sides, essentially creating a monolayer instead of a bilayer. This structure is much more resistant to pressure-induced disruption because the membrane is covalently bonded across its width, rather than being two separate layers held together only by weak, hydrophobic interactions. These tetraether lipids are found primarily in archaea, a domain of life distinct from bacteria and eukaryotes, living in extreme environments including deep-sea hydrothermal vents. The discovery of tetraether lipids opened up entirely new areas of research into membrane biochemistry and extremophile adaptations. Some deep-sea organisms also produce specialized sugars and sugar alcohols that function as osmolytes, similarly to TMAO but with different mechanisms. Glycerol, a simple 3-carbon sugar alcohol, accumulates in high concentrations in some deep-sea organisms and helps stabilize proteins and membranes. Trehalose, a disaccharide sugar, is found in elevated levels in some deep-sea invertebrates and is known to stabilize biological structures against various stresses including pressure. Betaine and sarcosine, small nitrogen-containing organic molecules, also function as osmolytes in various deep-sea species. The fact that evolution has converged on multiple different chemical solutions to the pressure problem suggests there is no single best answer, but rather a toolkit of useful molecules that different organisms employ in different combinations, depending on their specific physiology and evolutionary history. The energetic cost of producing these protective molecules is significant and represents a burden that deep-sea organisms must bear. TMAO synthesis requires cellular energy and biosynthetic machinery. High TMAO concentrations affect cellular osmotic balance, requiring compensatory changes in ion concentrations. The fact that organisms invest so heavily in TMAO production provides strong evidence that pressure adaptation is a major selective force in the deep sea, important enough to justify substantial metabolic cost. Organisms that fail to produce adequate protective molecules simply cannot survive at depth, while those that overproduce these molecules waste energy that could have gone to growth or reproduction. Natural selection optimizes the balance, favoring organisms that produce just enough protective molecules for their depth range, no more and no less. This optimization can be observed in the linear relationship between depth and TMAO concentration across species, a relationship so consistent it can be used to predict the depth range of a species from its tissue TMAO levels. One particularly interesting research direction involves studying organisms that undergo vertical migration, spending part of their time at depth and part near the surface. Many species of fish, squid, and crustaceans migrate vertically hundreds of meters every day, rising toward the surface at night to feed and descending to depth during the day to avoid predators. These vertically migrating organisms experience dramatic pressure changes twice daily, equivalent to what would cause severe decompression sickness in a human diver. How do they tolerate these rapid pressure changes? Research suggests several mechanisms. First, as we have discussed, they maintain pressure equilibrium by having no gas spaces, so pressure change creates no differential. Second, they likely have biochemistry that functions adequately across a range of pressures, rather than being optimized for a single pressure. Their proteins and membranes must be somewhat pressure insensitive compared to species that remain at constant depth. Third, they may adjust their osmolyte concentrations over time in response to changing depth, though this would be energetically costly and slow. Fourth, they simply tolerate some degree of biochemical inefficiency, functioning less than optimally at both surface and depth, but adequately enough to survive and reproduce. The vertical migrators represent a different evolutionary strategy than specialists, tolerating variation rather than precisely adapting to constant conditions. This generalist strategy has its own costs and benefits in the complex ecological interactions of the open ocean. Looking at the paleontological and evolutionary history of deep-sea life raises fascinating questions about when and how pressure adaptations evolved. The deep ocean has existed as long as liquid water has existed on Earth, billions of years. But when did life first colonize the deep sea? Fossil evidence from the deep sea is extraordinarily rare because deep-sea sediments are eventually subducted into the Earth's mantle at tectonic plate boundaries, destroying any fossils. We have almost no direct fossil record of ancient deep-sea ecosystems. However, molecular phylogenetics, studying the evolutionary relationships of living species through their DNA sequences, provides indirect evidence. Many deep-sea lineages appear to be quite ancient, having diverged from shallow water relatives hundreds of millions of years ago. This suggests deep-sea colonization happened relatively early in animal evolution, perhaps during the Cambrian explosion 540 million years ago, when most major animal groups first appeared. But the specific pressure adaptations we see today, like high TMAO concentrations and specialized proteins, probably evolved gradually over tens or hundreds of millions of years as lineages adapted more completely to deep-sea life. The genetic changes underlying these adaptations are being discovered through comparative genomics, comparing the complete DNA sequences of related shallow and deep-sea species to identify the specific genes and mutations responsible for pressure adaptation. This is a rapidly advancing field that will dramatically expand our understanding in coming decades. Some of the most exciting recent discoveries involve finding multicellular life at far greater depths than previously thought possible. In the 1950s and 60s, when deep-sea biology was in its infancy, many scientists believed complex multicellular life could not exist below about 6,000 meters. The pressures seemed too extreme, the food too scarce, the conditions too harsh. But systematic deep sampling has found animals much deeper. The discovery of snailfish below 8,000 meters was shocking. The capture of amphipods from nearly 11,000 meters at Challenger Deep was revolutionary, completely changing our understanding of life's limits. Each new depth record forces us to revise upward our estimates of where life can exist. And each discovery comes with new adaptations we had not seen before, new solutions to the pressure problem, new examples of evolution's creativity. Some researchers now speculate that the theoretical depth limit for multicellular animal life might be even deeper than 8,000 meters under certain conditions, perhaps 9 or even 10,000 meters if sufficient food were available, and if organisms could evolve even more effective pressure adaptations than those we currently know about. The question remains open and exciting. The deep sea also presents a fascinating natural laboratory for studying evolution in isolated populations. Deep-sea trenches are like islands, isolated habitats surrounded by slightly shallower regions that form barriers to dispersal for trench-specialized species. Populations in different trenches may be genetically isolated from each other for millions of years, evolving independently. This can lead to speciation, the formation of new species uniquely adapted to each trench. Comparing organisms from different trenches reveals how evolution produces similar solutions to similar problems independently, a phenomenon called convergent evolution, or alternatively how it produces different solutions depending on the starting genetic and ecological conditions. The deep-sea fauna represents millions of years of evolution in extreme conditions, a grand natural experiment in adaptation that we are only beginning to analyze using modern molecular tools. As we collect more samples and sequence more genomes from deep-sea organisms, we will gain unprecedented insights into the genetic basis of adaptation, the tempo and mode of evolution in extreme environments, and the fundamental constraints and possibilities that pressure places on the evolution of life. Now we arrive at one of the most genuinely fascinating and instructive aspects of deep sea pressure from a biological perspective. How organisms specifically adapted to live their entire lives at great depths managed to not just barely survive but actually thrive in conditions that would kill surface-dwelling creatures, including humans, absolutely instantly. The secret to their success lies in one elegantly simple principle that, once understood, makes everything clear. Eliminate all compressible air spaces from your body and ensure that your internal pressure perfectly matches external pressure at all times. Think carefully about a fish living at 3,000 meters depth, swimming around and feeding and reproducing at a location experiencing pressure of approximately 300 atmospheres. This fish, unlike a human, has no lungs whatsoever. It does not breathe air. Instead, it extracts dissolved oxygen directly from the water using gills, specialized organs where water flows over thin membranes, allowing oxygen to diffuse into the blood. The water inside the fish's body, permeating all its tissues and filling its body cavity, is at exactly the same pressure as the water outside its body. There is no pressure differential whatsoever between inside and outside. There are no air pockets anywhere that could potentially compress. When 300 atmospheres of pressure pushes inward on the fish, from absolutely all sides simultaneously, the fish pushes back outward with exactly 300 atmospheres of internal pressure. The forces balance perfectly, completely, at every point on and in the fish's body. The fish exists in perfect pressure equilibrium with its surrounding environment. There is no net pressure differential anywhere, so there is nothing trying to compress or crush anything. The fish's body is overwhelmingly water, approximately the same density and composition as seawater itself, and as we have established, water does not compress significantly, even at these enormous pressures. The result, the outcome of this simple but profound adaptation, is a fish that experiences absolutely no more discomfort from the surrounding 300 atmospheres of pressure than you or I experience from the 1 atmosphere of air pressure at sea level. The fish simply does not notice the pressure because it is in equilibrium with it. This fundamental principle extends uniformly throughout the entire deep-sea ecosystem, across every form of life that has successfully colonized those depths. Crabs scuttling across the seafloor, octopuses hunting in the darkness, segmented worms burrowing in sediments, translucent jellyfish drifting in the water column. Every single creature living at great depth shares this common essential adaptation. They have systematically eliminated or drastically minimized all gas-filled spaces within their bodies, and they maintain internal hydrostatic pressure perfectly equal to external environmental pressure at all times. Their bodies are composed primarily and almost entirely of incompressible liquids, mainly water, and incompressible solids, mainly proteins and minerals. They do not fight against the pressure in any sense, they match it precisely. They are in equilibrium. But the story of pressure and deep sea life does not end there with this simple mechanical equilibrium, because pressure profoundly affects biology in many subtle ways that go far beyond simple physical compression of volumes. While organisms can successfully avoid being physically crushed by eliminating air spaces and maintaining pressure equilibrium, the truly enormous pressures found at great depth still pose serious and potentially lethal biochemical challenges at the molecular level that must be overcome through specialized adaptations. Pressure fundamentally affects how molecules interact and bind with each other. It influences the delicate three-dimensional folding patterns of proteins, which depend on weak chemical bonds. It affects enzyme catalytic function and reaction rates. It changes the physical properties of cell membranes, making them more rigid. At the molecular level of individual atoms and chemical bonds, high pressure can distort and deform the precise shapes that proteins must maintain to perform their biological functions, interfering catastrophically with their ability to do their cellular jobs. High pressure can make cell membranes transition from a fluid state to a more solid gel-like state, like butter becoming hard and brittle when you put it in the refrigerator, preventing the membrane from functioning properly as a selective barrier. These pressure-induced biochemical effects would be immediately lethal to organisms adapted for surface conditions if deep-sea organisms had not evolved remarkable and sophisticated biochemical adaptations specifically to cope with them over millions of years of evolution. The most significant and well-studied of these biochemical pressure adaptations involves a small organic molecule with the intimidating chemical name trimethylamine N-oxide, universally abbreviated in scientific literature as TMAO for obvious convenience. TMAO has actually been known to chemists and marine biologists for a very long time as the specific organic compound primarily responsible for giving fish their characteristic fishy smell that anyone who has visited a fish market or a dock knows instantly. But only within recent decades, really within the last 30 or 40 years, have scientists gradually discovered and characterized TMAO's absolutely crucial protective role in enabling deep-sea organisms to withstand the otherwise destructive effects of high pressure on their cellular biochemistry. Trimethylamine N-oxide is what scientists categorize as a piezolyte, from the Greek word for pressure, or alternatively an osmolyte, both terms referring to small organic molecules that help stabilize proteins and other critical biological structures under extreme conditions, including high pressure. When researchers began systematically analyzing tissue samples from fish caught at various depths, they discovered something remarkable and highly suggestive. Deep-sea fish contain dramatically higher concentrations of TMAO in their muscle tissues compared to closely related fish species living in shallow water near the surface. And furthermore, the TMAO concentration increases in a remarkably predictable way with the depth at which the fish species normally lives. A fish caught at 4,000 meters depth might easily have 5 or 6 times more TMAO in its muscles than a related fish species caught in shallow coastal waters. This is not merely a coincidence or a random variation. The TMAO is actively, specifically protecting the deep-sea fish's proteins from pressure-induced structural damage that would otherwise kill the animal. At the detailed molecular level that biochemists study, high pressure disrupts and distorts the normal structure of water surrounding protein molecules. Water at normal surface pressure forms an organized tetrahedral network structure through hydrogen bonding between molecules, a beautifully ordered arrangement that gives water many of its unique and biologically essential properties. High pressure physically distorts this hydrogen bonding network, changing fundamentally how water molecules interact with the surfaces and crevices of dissolved proteins, and potentially causing those proteins to unfold or misfold into non-functional shapes, which would completely destroy their biological activity and kill cells. TMAO counteracts this pressure-induced water disruption through a fascinating molecular mechanism that researchers have only recently begun to understand in detail. The TMAO molecule has both hydrophobic regions that repel water, primarily the 3-methyl groups, and hydrophilic regions that attract water strongly, particularly the nitrogen-oxygen polar bond. The molecule is highly polarizable, meaning its internal charge distribution can shift and respond dynamically to its local chemical environment. When TMAO molecules dissolve in water at high concentration, they form very strong hydrogen bonds with nearby water molecules, hydrogen bonds that are actually significantly stronger than the normal water-to-water hydrogen bonds in pure water. These abnormally strong hydrogen bonds created by TMAO help stabilize and preserve the water's tetrahedral molecular structure, even when enormous external pressure tries to distort and collapse it. Think of TMAO functioning like a molecular brace or scaffold, physically holding the water structure together and preventing deformation even when crushing pressure acts from all sides. By preserving something closer to the normal surface pressure structure of water around proteins even at high pressure, TMAO allows those proteins to maintain their proper, carefully folded 3-dimensional shapes and continue functioning catalytically despite the crushing pressure of the deep-sea environment that would otherwise denature them. Recent sophisticated research combining experimental measurements with computer molecular modeling has even calculated something scientists call an osmolyte protection ratio. This is defined as the specific concentration of TMAO needed at each particular depth to precisely counteract the biochemical effects of pressure at that depth, maintaining normal protein function. Remarkably, when marine biologists measured actual TMAO concentrations in fish caught at systematically varying depths, they discovered that the fish naturally maintain this theoretically optimal protection ratio almost perfectly. Fish living at greater depths had proportionally more TMAO in their tissues, in almost exactly the amount needed to protect their proteins from the greater pressure they experience continuously. This extraordinarily precise matching strongly suggests that TMAO concentration is under intense evolutionary selection pressure, that natural selection over countless generations has exquisitely fine-tuned these organisms to produce exactly the right amount of this protective molecule for their specific depth environment, no more and no less than necessary. But even the remarkable protective powers of TMAO have fundamental physical limits, beyond which biochemistry simply cannot function. At extreme depths approaching and exceeding 8,000 meters, even maximum possible TMAO concentrations begin to lose their protective effectiveness, as pressure becomes simply too great to counteract by any chemical means. Some marine biologists and biochemists believe this might represent a fundamental biochemical depth limit for complex multicellular life, a hard physical ceiling beyond which the laws of chemistry and physics simply will not permit proteins to function properly no matter what protective molecules are present. Beyond this critical depth, pressure becomes so utterly extreme that even with maximum TMAO protection at saturation concentration, essential proteins begin to fail and denature irreversibly, and cells can no longer maintain the chemical reactions necessary for life. This hypothetical biochemical depth limit could potentially explain a puzzling observation: why the very deepest parts of the ocean, the Hadal trenches below 8,000 meters, seem to have noticeably reduced biodiversity and biomass, compared to the somewhat shallower abyssal plains between 4,000 and 6,000 meters, though isolated organisms have definitely been found and filmed even in the deepest trenches using advanced robotic landers. The deepest fish species ever discovered and scientifically documented, a gelatinous snailfish found in the Mariana Trench at depths exceeding 8,100 meters, may very well represent something close to the absolute limit of where vertebrate life, with its complex protein-based biochemistry, can possibly exist under Earth's conditions. This remarkable fish has evolved an absolutely extraordinary suite of physiological and biochemical adaptations specifically to survive in such otherwise impossible conditions. Its body is soft and gelatinous almost to the point of formlessness, with very little calcification or hardening in its skeletal structures. Traditional rigid, well-calcified bones like those found in shallow water fish would actually be a serious liability at such crushing depths. Instead, the Hadal snailfish has bones made almost entirely of flexible cartilage, soft, bendable structures that can compress and deform slightly without shattering or fracturing under pressure. Its skull has large gaps and openings where bone has been evolutionarily eliminated entirely, spaces that look like structural weaknesses but actually serve a crucial pressure equalizing purpose. These gaps help equalize pressure between the inside and outside of the skull, preventing any pressure differential from building up that could cause crushing damage to the brain. The snailfish also maintains extremely high concentrations of TMAO and similar protective molecules in all its tissues, likely approaching the maximum possible concentration that cells can tolerate. Its body is almost entirely water, maybe 95% or more, with very little dense protein-rich tissue. It looks almost translucent, like a living blob of gel with minimal structural framework when photographed. This body plan minimizes the amount of structural material that needs to be mechanically supported and dramatically reduces the energetic cost of maintaining any structural integrity under such pressure. The fish has evolved specialized variant proteins that are intrinsically more resistant to pressure-induced denaturation than normal proteins, requiring less TMAO protection to maintain function. It has lost all functional eyes, since vision is completely useless in the absolute eternal darkness of the deepest trenches where sunlight has never penetrated. Every aspect of its biology has been evolutionarily stripped down, simplified, and optimized specifically and exclusively for survival in this most extreme environment. These creatures represent evolution pushed to its absolute physical limits, life desperately clinging to existence right at the boundary of what the laws of physics and chemistry permit. They remind us powerfully that life, given sufficient time and relentless selection pressure, can adapt to almost anything, can find ingenious ways to thrive in environments that seem utterly hostile to everything we think we know about biology and livable conditions. Now let us turn our attention to the diving mammals, the whales, and seals and dolphins that present a unique and fascinating pressure challenge compared to fish. These creatures face difficulties that fish simply do not encounter. Unlike fish, marine mammals breathe air and have lungs, true lungs similar in basic structure to human lungs. They cannot eliminate gas spaces from their bodies entirely. They must surface regularly to breathe. Yet some of them dive to absolutely extraordinary depths that seem impossible for air-breathing animals. The Cuvier's beaked whale currently holds the scientifically verified record for the deepest dive by any marine mammal, reaching a staggering 2,992 meters down, nearly 2 full miles straight down into darkness, and remaining submerged holding its breath for an incredible 2 hours and 18 minutes. Sperm whales regularly dive to depths exceeding 2,000 meters and routinely stay underwater for 60 to 90 minutes hunting giant squid in the darkness. How do these air-breathing, lung-possessing animals possibly survive pressures that would collapse and destroy human lungs catastrophically in seconds? The answer involves some of the most remarkable physiological adaptations found anywhere in the entire animal kingdom. Adaptations that push the boundaries of what seems physiologically possible for an air-breathing, warm-blooded vertebrate. Let us start our examination with the lungs themselves, since lungs are the obvious problematic air-filled space. Human lungs, if suddenly subjected to deep ocean pressure without gradual acclimation or protective measures, would undergo catastrophic collapse, causing immediate severe pulmonary barotrauma, hemorrhaging, and death. But diving mammals have evolved lungs and rib cages with a fundamentally different architecture than terrestrial mammals. Their lungs are collapsible by design. As a whale or seal descends and external pressure increases steadily, its lungs compress gradually and in a controlled fashion rather than catastrophically rupturing. The rib cage is remarkably flexible, not rigid like human ribs, allowing the entire chest cavity to shrink progressively as the lungs collapse without breaking bones. Eventually, at sufficient depth, the mammal's lungs collapse almost completely, becoming flattened sacs with minimal volume. But here is the truly ingenious adaptation, the clever evolutionary trick that makes deep diving possible. Before beginning a deep dive, the whale or seal exhales most of the air from its lungs while still at the surface. It dives with lungs that are perhaps only 10% full or even less, having deliberately emptied them. As it descends and the lungs collapse further under increasing pressure, the small remaining volume of air is not compressed in the alveoli, those microscopic air sacs deep in the lung tissue where gas exchange between air and blood normally occurs. Instead, the air is progressively forced out of the collapsible alveoli and into the trachea and bronchi, the relatively rigid cartilage-reinforced airways leading to the lungs, where gas exchange cannot and does not occur because there are no blood vessels there. This means that at depth, even though there is still some air in the respiratory system, that air is isolated in the non-functional airways and is not in contact with blood, so no gas exchange happens. This anatomical trick is absolutely crucial for preventing what divers know and fear as the bends, also called decompression sickness. When a human scuba diver breathes compressed air at depth, the dramatically increased pressure forces nitrogen from the air to dissolve into the blood in much greater quantities than normal, following Henry's law, which states mathematically that the amount of gas that dissolves into a liquid is directly proportional to the partial pressure of that gas above the liquid. At 10 meters depth, where pressure is 2 atmospheres, twice as much nitrogen dissolves in the blood compared to the surface. At 100 meters and 11 atmospheres, 11 times as much nitrogen saturates the blood and body tissues. If that diver then ascends too rapidly toward the surface, the pressure drops quickly, and the dissolved nitrogen comes rapidly out of solution, forming microscopic bubbles in the blood and tissues like opening a shaken soda bottle. These nitrogen bubbles can physically block blood vessels, preventing blood flow to tissues. They can accumulate in joints, causing excruciating pain. They can damage the spinal cord, causing paralysis. They can form in the brain, causing strokes. They can cause death. This is the bends decompression sickness, and it represents a serious, ever-present danger for any human diver breathing compressed gas at depth. But deep-diving whales and seals completely avoid this problem through their collapsible lung adaptation, because they stop exchanging gas with their lungs once they reach depth. No gas exchange means no additional nitrogen dissolving into the blood beyond what was already there from the surface breath, which means essentially no risk of dangerous bubble formation during ascent, because there is no excess dissolved gas to come out of solution. So if these diving mammals are not breathing at depth and not exchanging respiratory gases with their environment, how do they possibly obtain enough oxygen to fuel their metabolism and stay conscious during dives that last an hour or more? The answer is sophisticated oxygen storage. Diving mammals have dramatically and spectacularly higher concentrations of hemoglobin in their blood compared to terrestrial mammals like humans, sometimes double or triple the concentration. Hemoglobin is the iron-containing protein in red blood cells that binds oxygen and carries it throughout the body. They also have much higher concentrations of myoglobin in their skeletal muscles. Myoglobin is a related protein that stores oxygen specifically in muscle tissue. A sperm whale might have total blood volume 3 to 4 times greater per kilogram of body weight than a human, and that blood has far higher oxygen carrying capacity per milliliter. Before a dive, the whale surfaces and breathes rapidly and deeply for several minutes, hyperventilating to completely saturate its blood and muscles with as much oxygen as physically possible, loading its biological oxygen tanks to maximum capacity. Then it dives, relying entirely on this stored oxygen to fuel its metabolism throughout the entire dive with no additional oxygen input. The animal is essentially holding its breath, but with vastly greater oxygen storage capacity than any terrestrial animal. To make this limited stored oxygen last as long as possible during extended deep dives, diving mammals employ several additional remarkable physiological tricks and adaptations. During a dive, their heart rate slows dramatically through a reflex response, sometimes dropping to just 2 or 3 beats per minute from a resting rate that might be 60 beats per minute at the surface, a phenomenon called bradycardia. This drastic reduction in heart rate significantly reduces the body's overall oxygen consumption rate. Simultaneously, blood flow is selectively restricted through vasoconstriction to non-essential tissues and organs, maintaining full blood supply only to the absolutely critical organs that must have oxygen to prevent permanent damage, the heart muscle itself, the brain, and a few other vital structures. Less critical tissues like skeletal muscles and digestive organs must make do with minimal blood flow, or must switch entirely to anaerobic metabolism, producing energy through chemical pathways that do not require oxygen, but generate lactic acid as a waste product. The diving animal essentially shuts down all non-essential body functions, entering a state of profound metabolic depression, conserving its precious limited oxygen supply for as long as physically possible. When the whale or seal finally surfaces after its deep dive, having depleted most of its oxygen stores, it must immediately and urgently repay what physiologists call its oxygen debt. The animal breathes rapidly and forcefully at the surface, its famous blow sending spray and vapor high into the air as it exhales with tremendous force to expel carbon dioxide and then inhales deeply to refill its lungs, repeating this breathing cycle dozens or even hundreds of times to reload its blood and muscle oxygen stores back to capacity. The muscles that operated anaerobically during the dive must now process and metabolize accumulated lactic acid, which requires oxygen. The organs and tissues that received minimal blood flow during the dive must recover their normal function and repair any minor damage from temporary hypoxia. This recovery period at the surface is absolutely crucial for the animal's survival, and the whale cannot safely dive again deeply until its body has sufficiently recharged its oxygen stores and cleared metabolic waste products. The physiology of deep-diving marine mammals represents perhaps the most extreme and sophisticated adaptation to pressure challenges that any air-breathing animal has ever achieved through evolution. These creatures have pushed the physiological boundaries of what seems physically possible, evolved extraordinarily complex integrated solutions to problems that human engineers would struggle enormously to solve artificially. They stand as living testaments to the power of natural selection over deep time to shape organisms for survival and success in even the most challenging environments imaginable. Let us shift our focus now to human encounters with deep sea pressure throughout history and the often tragic lessons learned about pressure's power and the harsh limits of human engineering in hostile environments. The history of deep-sea exploration is absolutely filled with narrow escapes, close calls, and outright disasters that taught us painful lessons about pressure's destructive capabilities and the unforgiving nature of the deep ocean. One of the earliest and most courageous pioneers of deep-sea exploration was William Beebe, a naturalist, explorer, and gifted writer who in the 1920s and 30s began conducting revolutionary experiments with deep-sea descents in a device called the bathysphere. The bathysphere was an almost absurdly simple, yet terrifying contraption. A hollow steel ball barely large enough in diameter for two people to squeeze inside uncomfortably, with steel walls several inches thick to resist external pressure, and tiny circular quartz windows just a few inches across for viewing the outside world. The sphere was lowered into the ocean suspended on a steel cable, a completely passive descent with no independent propulsion system, no motors, no way to return to the surface except to be physically winched back up by the ship above. Beebe and his engineer collaborator Otis Barton set depth records repeatedly during the early 1930s, descending to over 900 meters by 1934, deeper than any human being had ever gone before and lived to tell about it. The psychological terror of those descents is almost impossible for us to truly comprehend sitting safely on land. You sit cramped and curled up in a metal sphere in total darkness, except for whatever your external lights happen to illuminate in the murky water, knowing with absolute certainty that the cable above you is your only lifeline connecting you to the surface and survival, feeling and hearing the metal sphere creak and groan ominously as external pressure increases with each meter of descent. You pass slowly through layers and zones of ocean life, seeing bizarre creatures that no human eye has ever seen before, and all the while you cannot help but wonder whether the hull will hold, or whether a window will suddenly crack and seawater will blast inward with such incredible force that you would be killed instantly before you could even scream for help. Beebe wrote vividly and movingly in his published accounts about his experiences in the bathysphere. On one particularly unnerving occasion after a deep dive, when they brought the bathysphere back safely to the surface and began the process of opening the hatch, he started to unscrew the giant wing bolt that held the door sealed shut, and after the first few careful turns of the bolt, a strange high, musical singing sound came forth from the seal, followed immediately by fine mist, steam-like in consistency, shooting out in thin needle-like jets. Then another jet appeared, and another. This dramatic and unexpected phenomenon warned him clearly that he should have realized when looking through the window earlier that the contents of the sealed bathysphere were under tremendous internal pressure from the dive. During the deep descent, even the air inside the sphere had been compressed significantly by the external pressure transmitted through tiny flexing of the thick steel walls. When he began releasing that pressure by loosening the seal, the compressed air expanded rapidly, and water vapor in that air condensed suddenly in the rapid pressure drop, creating visible jets of steam. Beebe had to very carefully and slowly clear the deck area in front of the door of all personnel, crew and scientists alike. He set up motion picture, cameras at safe distances to document what happened next. Then, leaning back as far as physically possible from the direct line of fire, He and a colleague very carefully turned the brass handles in tiny increments, continuously listening as the high, musical tone of escaping compressed air gradually descended the musical scale, perhaps a quarter tone or less at each slight turn of the handle. They fully realized what catastrophe might occur if they released the pressure too quickly. Eventually, after careful work, the internal pressure equalized with the outside and the hatch could be safely opened. On another absolutely terrifying occasion during their pioneering work, they tested the bathysphere unmanned to depth as a safety precaution, and when it returned to the surface, they discovered to their horror that a thin needle-like jet of water was spraying forcefully across the interior, shooting across one of the thick quartz windows. The window seal had developed a microscopic leak at depth. If that tiny leak had occurred with Beebe and Barton trapped inside the sealed sphere at depth, the result would have been utterly catastrophic and unsurvivable. At the tremendous depth they had reached, the pressure differential between outside and inside would have driven seawater through even a hairline crack, with cutting force like a water jet cutter. The high-pressure stream would rapidly erode the crack larger and larger. Within seconds or at most minutes, the window frame would fail completely and catastrophically, and the entire sphere would flood instantly with crushing seawater, killing both occupants before they could react. The sphere was hastily hauled back to the surface, and the window carefully examined by engineers. It was immediately apparent that the external pressure during that particular test dive had been very nearly too much for that specific window to withstand, that they had pushed dangerously close to the absolute limit of what the materials and design could tolerate. These early pioneering expeditions also revealed another terrifying and completely unexpected aspect of deep diving that had not been fully anticipated or understood: the effect of depth and pressure on human psychology and mental function. During at least one deep bathysphere dive, one of Beebe's crew reported experiencing strange mental effects while at depth, becoming emotionally unstable or mentally foggy in ways that were difficult to describe clearly, experiencing effects that vanished mysteriously upon return to normal surface pressure. This was quite likely an early first-hand observation and documentation of what modern dive medicine now calls nitrogen narcosis, though the full understanding of this dangerous phenomenon and its biochemical mechanisms would not come until decades later with systematic research. Nitrogen narcosis, colloquially and rather poetically called rapture of the deep or sometimes the Martini effect, is a strange and genuinely dangerous condition that affects divers breathing compressed air at significant depth. The subjective experience feels remarkably similar to being drunk or mildly sedated, and it happens because of how high partial pressure of nitrogen gas affects the nervous system and brain function. At the ocean surface under normal atmospheric conditions, nitrogen makes up approximately 78% of the air we breathe with every breath. It is classified as an inert gas, meaning it does not normally participate in chemical reactions in the body under normal conditions. It simply dissolves in small quantities in the blood and body tissues, causing no noticeable physiological effects whatsoever. But as a diver descends into deeper water, the partial pressure of nitrogen in the breathing gas increases proportionally with total pressure. Partial pressure, an important concept in gas physics, is defined as the pressure contributed by one specific gas component in a mixture of gases. At 10 meters depth, where total pressure is 2 atmospheres, the partial pressure of nitrogen roughly doubles compared to its value at the surface. At 30 meters depth, total pressure is 4 atmospheres, and nitrogen partial pressure is approximately 4 times its surface level. When nitrogen partial pressure gets high enough in the blood, and particularly in the lipid-rich tissues of the nervous system, something strange and not entirely understood begins to happen at the cellular level. The dissolved nitrogen begins to act pharmacologically as an anesthetic agent, similar in many ways to how nitrous oxide, commonly known as laughing gas, works to sedate patients. The exact biochemical mechanism of action is still not completely understood even today, despite decades of research, but nitrogen at high partial pressure appears to interact with and disrupt nerve cell membranes and certain neurotransmitter receptor proteins, particularly GABA receptors, altering how neurons fire electrical signals and communicate chemically with each other. The result is a characteristic set of symptoms and behavioral changes that can be quite subtle and barely noticeable at first, but become increasingly severe and dangerous with increasing depth. At around 30 meters depth, many divers begin to notice mild effects of nitrogen narcosis, a feeling of mild euphoria or unusual well-being, slight slowing of thought processes and reaction time, reduced concern about potential danger, poor judgment. Some individual divers feel essentially nothing at this depth. Susceptibility varies widely from person to person, but as depth continues to increase, nitrogen narcosis affects absolutely everyone eventually. At 60 meters depth, symptoms typically become quite pronounced and obvious. Seriously poor judgment and decision-making, significantly slowed reaction time, difficulty performing even moderately complex tasks, confusion about depth or time or dive plan. The diver might feel absolutely wonderful, blissfully unconcerned about anything, even while their cognitive ability to think clearly deteriorates dangerously. At 100 meters depth, while breathing regular compressed air, a diver would be severely impaired mentally, possibly unable to perform even simple tasks like checking gauges or manipulating equipment, functioning at the level of someone extremely intoxicated on alcohol. The narcosis can progress to complete unconsciousness and death at sufficient depth if the diver continues descending. The particularly insidious and genuinely deadly danger of nitrogen narcosis lies specifically in its powerful effect on judgment and self-awareness. A severely narked diver often does not realize that they are impaired or that their thinking is compromised. They might subjectively feel absolutely fine, better than fine, even wonderful and euphoric, even while simultaneously making catastrophic decisions that will kill them. They might choose to swim deeper instead of recognizing they need to ascend immediately to shallower water. They might completely ignore their air supply gauge showing that they are running dangerously low on breathing gas. They might inexplicably remove their regulator from their mouth, or make other bizarre illogical choices that would be obviously suicidal if they were thinking clearly with their normal mental faculties. This is precisely why nitrogen narcosis is sometimes informally and half-jokingly called the martini effect in diving communities. Each additional 10 meters of depth is humorously compared to drinking one alcoholic martini at a bar, with all the attendant progressive loss of motor coordination and mental judgment that comes with each drink. The phenomenon of nitrogen narcosis was first systematically described and studied by naval diving researchers in the mid-20th century during and after World War II. During the war, military divers needed to operate at greater and greater depths for salvage operations, underwater construction, and submarine rescue, pushing beyond the relatively shallow limits of earlier diving work. They began reporting strange and concerning experiences at depth, feeling drunk or confused, having serious difficulty with simple arithmetic or basic procedures, forgetting fundamental training. Controlled experiments in pressure chambers confirmed scientifically that cognitive function declined measurably and predictably with increasing depth when breathing compressed air. The practical solution for dives much deeper than 100 meters is to replace some or all of the nitrogen in the breathing gas mixture with helium. Helium is also an inert gas but does not cause narcosis because it is much less soluble in nerve tissue and does not interact with neural membranes in the same way nitrogen does. A diver breathing heliox, which is a carefully mixed helium-oxygen blend, can descend to much greater depths without experiencing narcotic effects from the breathing gas itself. Technical divers planning deep penetration dives use incredibly complex custom gas mixtures called trimix that include helium, nitrogen, and oxygen in carefully calculated proportions to minimize nitrogen, partial pressure at depth, while maintaining safe oxygen levels and avoiding oxygen toxicity and other diving hazards. But for recreational sport divers using simple compressed air from standard scuba tanks, nitrogen narcosis remains a very real concern and hazard. Dive training courses emphasize strongly staying within conservative depth limits, where narcosis is unlikely to be severe, typically 30 meters or less for recreational diving. Divers are explicitly taught to recognize the early warning symptoms of narcosis in themselves and to watch for behavioral signs in their dive buddies, and to ascend immediately to shallower depth if narcosis is suspected in anyone. The wonderful news is that the effects of nitrogen narcosis disappear completely within just minutes of ascending to shallower depth, leaving absolutely no lasting physiological harm if caught in time before the narsed diver does something fatally stupid. Nitrogen narcosis is just one of several serious pressure-related physiological dangers that human divers must constantly be aware of and manage carefully. The bends, also known as decompression sickness as we discussed earlier, is another ever-present threat. Carbon dioxide buildup in the blood, called hypercapnia, is yet another concerning hazard, because breathing resistance increases significantly with depth due to the increased density of compressed gas, making it physically harder to move air in and out of the lungs, and a diver working very hard at depth might find they simply cannot breathe fast enough to adequately eliminate carbon dioxide waste from their metabolism, leading to elevated CO2 levels in the blood, which causes symptoms ranging from headache and mental confusion to complete loss of consciousness. And then there is oxygen toxicity, which surprisingly and counterintuitively can kill you at depth. At high partial pressures significantly above 1 atmosphere, oxygen itself becomes chemically toxic to the central nervous system and lungs, causing seizures that would obviously be immediately fatal underwater where the diver would drown. For all these complex interrelated reasons, human divers using breathing apparatus face strict physiological depth limits based on the specific gas mixture they are breathing and the total duration of the dive. Commercial and military divers operating at significant depths use incredibly complex decompression tables and sophisticated dive computers to calculate safe dive profiles, carefully balancing depth, bottom time, and gas mixture composition to avoid all the various physiological hazards. Saturation divers, who live continuously in pressurized habitats for weeks at a time, while making repeated daily excursions to depths of several hundred meters for underwater construction, or oil rig maintenance, must undergo extremely long controlled decompression periods, lasting many days to very slowly eliminate dissolved gases from their tissues and avoid the bends when finally returning to surface pressure. The logistical complexity and inherent physiological danger of deep human diving makes it abundantly clear why we increasingly rely on unmanned, remotely operated vehicles for the deepest ocean exploration work. The pressure-related physiological challenges are simply too great and too dangerous for the fragile human body to handle safely beyond certain depth limits. But humans understandably still want to visit the deep ocean directly with their own eyes, rather than through camera feeds, so marine engineers have progressively developed increasingly sophisticated and capable manned submersibles over decades. Modern research submersibles like Alvin, which has been continuously operating since the 1960s and has made thousands of successful dives, use spherical pressure hulls manufactured from titanium alloy. The sphere is the mathematically and structurally optimal shape for resisting omnidirectional external pressure because the pressure load is distributed absolutely evenly across the entire curved surface with no stress concentrations at sharp corners or edges that could initiate cracks. Titanium alloy is specifically chosen for its exceptional strength-to-weight ratio, making it light enough to be practical, while strong enough to resist enormous pressure, and for its excellent resistance to corrosion in seawater. The pressure hull is typically several inches thick, solid titanium metal capable of withstanding many thousands of pounds per square inch of external pressure while maintaining structural integrity. Inside this protective metal sphere, the human crew breathes normal air at comfortable 1 atmosphere pressure, remaining safe and comfortable, while outside the hull the external pressure may be hundreds of atmospheres greater. Viewports, called portholes in traditional nautical terminology, are among the most challenging and failure-prone components of any deep submersible design. Regular glass or acrylic plastic would shatter instantly under the enormous pressure differential at depth, so viewports must be manufactured from extremely thick blocks of synthetic sapphire or specialized polymer materials, shaped in a carefully designed truncated cone geometry, where the narrow small end faces toward the interior cabin and the wide large end faces toward the external ocean. As external pressure increases during descent, the conical viewport is pressed more and more firmly into its mounting seat, creating a progressively tighter seal, rather than trying to blow the viewport outward, which would cause catastrophic failure. Even so, viewports remain the structurally weakest point of any deep submersible and must be meticulously inspected before every single dive. The submersible must also be very carefully designed to achieve precise neutral buoyancy at its operating depth. If the vehicle were significantly denser than seawater, it would sink uncontrollably toward the bottom. If it were less dense than seawater, it could not descend without enormous downward thrust from propellers. Achieving exact neutral buoyancy is surprisingly tricky because seawater density varies measurably with temperature and salinity at different depths and locations, and because external pressure actually compresses the submersible hull slightly during descent, changing its volume and therefore its displacement. Designers use a specialized material called syntactic foam which is manufactured from countless tiny hollow glass microspheres carefully embedded in epoxy resin matrix, creating a material that is remarkably light yet extremely strong and nearly incompressible even at great depth. By carefully balancing the weight of the heavy steel or titanium pressure hull and all the equipment inside against the buoyancy provided by syntactic foam blocks attached to the exterior, the submersible can be engineered to achieve neutral buoyancy at its intended maximum operating depth. Descent from the surface is controlled by releasing or dropping expendable ballast weights. Ascent back to the surface is achieved by dropping additional ballast weights to make the vehicle positively buoyant. Horizontal propulsion and precise positioning comes from small electric thrusters mounted around the vehicle's exterior, allowing the submersible to move carefully in all directions and hold position precisely above interesting features. Life support systems continuously scrub carbon dioxide from the cabin air, add fresh oxygen to replace what the crew breathes, and maintain comfortable temperature and humidity inside the pressure hull. Battery power is inherently limited by weight and volume constraints, typically allowing mission durations of 8 to 12 hours maximum before the submersible must return to the surface and be recovered. Every critical system has multiple levels of redundancy built in for safety. If the submersible loses all electrical power, it is designed to naturally float back to the surface through careful buoyancy engineering. If thrusters fail completely, ballast weights can still be manually dropped to force emergency ascent. If the normal descent weight release mechanism fails, there are pyrotechnic explosive bolts that can be electrically triggered to forcefully separate the weights. The total amount of engineering expertise and careful redundant design that goes into making a safe, reliable, deep-sea submersible is absolutely staggering. And even with all these elaborate precautions and safety systems, deep dives remain inherently risky and dangerous operations. The tragic Titan disaster illustrated with horrible clarity what happens when corners are cut in submersible design and safety protocols are ignored. The ill-fated vessel used a carbon fibre and titanium composite hull in an unconventional cylindrical shape, rather than the proven traditional spherical design used by essentially all other successful deep submersibles. Carbon fibre composite has excellent tensile strength when properly manufactured and maintained, but it can fail catastrophically and unpredictably under repeated compression cycles, and microscopic damage accumulates invisibly inside the material with each dive. The cylindrical shape creates stress concentrations at the cylinder ends that a perfectly spherical hull completely avoids. The viewports were reportedly larger in diameter than conservative industry standards recommended for the extreme operating depth. Multiple warning signs about potential design flaws were allegedly raised by engineers and safety experts, but were apparently ignored by management. When the inevitable catastrophic failure finally occurred, the implosion was so rapid and so violent that it would have been completely over in milliseconds, faster than human nerve fibers could transmit pain signals to the brain. The only conceivable mercy in such a failure is its incomprehensible speed, death so fast that consciousness likely ceased before any awareness of the disaster. The harsh lesson from the Titan tragedy is that the deep ocean is fundamentally and absolutely unforgiving, that pressure is a relentless physical force that will ruthlessly exploit any weakness or flaw in design or materials, and that there is absolutely no room for hubris or cost-cutting or schedule pressure when designing equipment intended to protect human lives in these extreme conditions. The organizations that have successfully operated deep submersibles safely for many decades, like Woods Hole Oceanographic Institution with Alvin, do so only through absolutely rigorous testing protocols, extremely conservative engineering design with large safety margins, and absolute unwavering adherence to safety procedures and maintenance schedules. The ocean simply does not care about your confidence, or your business model, or your schedule. It will kill you instantly and without warning if given the slightest opportunity through carelessness or hubris. Let us return now to one of the most visually striking and memorable demonstrations of pressure's enormous power that has become a beloved tradition on oceanographic research vessels, the styrofoam cup shrinking experiment. This has become an almost universal custom on research ships equipped with deep-diving, remotely operated vehicles or manned submersibles. Before a dive to great depth, sometimes to depths of 3 or 4 or 5,000 meters, crew members and scientists decorate ordinary polystyrene foam coffee cups with colorful drawings, heartfelt messages, elaborate artwork, or personalized designs using permanent markers. The decorated cups are then securely attached to the outside of the diving vehicle, usually in a mesh bag tied to the exterior frame and sent down to the ocean floor, along with the vehicle. When the vehicle returns hours later to the surface and is recovered onto the ship, the foam cups come back dramatically and almost comically shrunken, compressed to perhaps 1/10 or less of their original size, but with all the decorations and artwork perfectly preserved and recognizable, just miniaturized like something from a fantasy story. The cups become tiny, dense versions of themselves, permanent souvenirs and keepsakes of the deep dive. What has actually happened to cause this transformation? Regular foam coffee cups are made of polystyrene polymer that has been mechanically puffed and expanded full of air bubbles during manufacturing, creating a lightweight cellular structure that is perhaps 95% air by volume and only 5% actual solid polystyrene. As the cup descends attached to the vehicle, external pressure steadily increases. At 2,000 meters depth, external pressure is approximately 200 atmospheres. The countless tiny air bubbles trapped inside the foam's cellular structure are compressed in volume to 1/200th of their original size, according to the gas laws we discussed earlier. The solid polystyrene material itself is virtually incompressible and does not change, but the air-filled spaces between polystyrene strands collapse dramatically. The foam structure collapses inward uniformly from all directions. The result is a cup that retains its basic shape and all surface features perfectly, but at a drastically reduced size, like a perfect scale model. The cup's mass has not changed at all. Every molecule of polystyrene is still present, but its volume has decreased enormously as the compressible air is squeezed out. When brought back to surface pressure, the air has escaped permanently through the compressed polystyrene matrix, and the cup remains shrunken because the foam's cellular structure has been irreversibly deformed and cannot re-expand. This simple experiment is actually a perfect demonstration and teaching tool for several important principles we have discussed throughout this exploration. First, and most obviously, it shows dramatically that pressure acts powerfully on compressible materials like gas-filled foam. Second, it beautifully illustrates that the compression is truly omnidirectional and uniform. The cup shrinks proportionally in all three dimensions rather than being flattened in any particular direction. Third, it reveals the dramatic quantitative power of pressure at depth, showing how 200 atmospheres of pressure is enough to compress foam dramatically, but importantly not enough to damage or deform truly incompressible solid materials. If you sent down a solid steel cube, it would return virtually unchanged. If you sent down a sealed rigid container with air inside at 1 atmosphere, it would either implode violently as the pressure differential exceeded the container's strength, or if the container was strong enough, it would survive completely intact with the compressed air still sealed inside. Only materials with internal compressible structure like foam show this dramatic uniform shrinking behavior. The styrofoam cup experiment has delighted oceanographers, submersible pilots, and research vessel crews for many decades. Some research vessels maintain permanent collections of hundreds of these tiny cups displayed in cases, each one marking and commemorating a particular notable dive or expedition. They serve simultaneously as scientific demonstrations of pressure principles and as whimsical personal keepsakes and conversation starters. They remind us wonderfully that the ocean is not solely a place of danger and tragedy and death, but also a realm of wonder and discovery and joy. Even something as mundane and disposable as a foam coffee cup can teach us profound lessons about physics and pressure when exposed to the deep sea's extraordinary conditions. Now let us explore a more abstract and theoretical question that fascinates biologists. What is the absolute deepest depth that life can possibly exist? We have discussed fish living at 8,000 meters depth and the crucial biochemical role of TMAO in protecting proteins from pressure damage. But is there a fundamental physical limit, a hard ceiling imposed by the laws of chemistry and physics, where pressure simply becomes too great for any conceivable form of life to function, where no amount of biochemical adaptation or evolutionary innovation can overcome the destructive effects of compression at the molecular level? This question has fascinated marine biologists, biochemists, and oceanographers for decades. The deepest zone of the ocean, extending from about 6,000 meters down to the very bottom of the deepest trenches at nearly 11,000 meters, is called the Hadal Zone. The name derives from Hades, the ancient Greek god of the underworld, Because these crushing depths represent Earth's most remote and hostile and least accessible frontier, an alien environment right here on our own planet. Life has definitely been found throughout the Hadal Zone despite the extreme conditions. Small crustaceans called amphipods, which look somewhat like shrimp, have been captured by baited traps from Challenger Deep at nearly 11,000 meters depth, the deepest point known on Earth. Microorganisms, bacteria and archaea almost certainly exist even deeper than this, thriving in the sediments at the very bottom of trenches where they likely feed on organic debris that slowly settles from above. But fish, vertebrate animals with complex physiology, seem to have a definite depth limit. The deepest fish species ever found and scientifically documented was discovered at about 8,134 meters depth in the Mariana Trench. Below this depth, no fish have been observed despite extensive searching with cameras and traps. Why would fish specifically disappear at this depth? 1. Compelling hypothesis centers specifically on TMAO concentrations and the physical limits of pressure stability for complex proteins. As we have discussed extensively, TMAO helps stabilize and protect proteins under high pressure, and fish species living at progressively greater depths maintain progressively higher tissue TMAO concentrations to protect themselves. But TMAO itself imposes biological costs and has upper limits. Very high TMAO concentrations can interfere with other aspects of cellular biochemistry and metabolism. And critically, at truly extreme pressures, even maximum possible TMAO concentrations cannot fully protect proteins from pressure-induced deformation and denaturation. Biochemists have calculated theoretically that somewhere around 8,000 to 8,500 meters depth, corresponding to roughly 800 to 850 atmospheres of pressure, the crushing pressure becomes so overwhelmingly great that even saturating concentrations of TMAO are simply overwhelmed and can no longer effectively protect proteins from unfolding. Proteins begin to denature irreversibly despite maximum TMAO presence. Cell membranes become too disrupted to function as selective barriers. The fundamental biochemistry required for complex animal life simply cannot function reliably anymore. This theoretical biochemical depth limit calculated from first principles corresponds remarkably well with the observed maximum depth for fish, around 8,100 meters, suggesting strongly that researchers have identified a true hard physical barrier. But invertebrate animals like amphipods demonstrably exist deeper than fish do, sometimes much deeper. Why can they survive where fish cannot? The answer likely lies in metabolic simplicity and lower biochemical demands. Amphipods and other deep hadal invertebrates have simpler, less complex protein biochemistry than vertebrate fish. They may require less precise protein function or less sophisticated enzyme activity to survive and reproduce. They may have evolved entirely different pressure adaptation strategies beyond TMAO that we do not yet fully understand. They might use combinations of different osmolytes and protective molecules working together. Their metabolic rate in the cold, high-pressure hadal environment is extremely low, drastically reducing the biochemical demands on their cellular machinery. They survive at the very edge of what is physically possible, but they do survive. For single-celled microorganisms, bacteria and archaea, the physical limits might be different still. Bacteria have far simpler cellular structures than complex animals. A bacterial cell is essentially a bag of enzymes with a chromosome, lacking the complex organelles and compartments of animal cells. They can reproduce extremely rapidly when conditions permit, allowing rapid evolution of new adaptations. Some deep-sea pressure-adapted microbes have been found to possess unique membrane lipid compositions that remain fluid under crushing pressure, or specialized variant proteins that are intrinsically more resistant to pressure deformation. The ultimate question of life's absolute depth limit remains partially open and actively researched. We know with certainty that vertebrate fish life stops around 8,000 meters. We know that invertebrate animals persist to at least 11,000 meters at Challenger Deep. Microbial life might potentially exist even in subsea floor sediments at greater depths and pressures, though sampling such environments at the deepest trenches is extraordinarily difficult and expensive. Theoretical calculations from physical chemistry suggest that at some pressure, probably far exceeding anything found in Earth's oceans, pressure would become fundamentally incompatible with any biochemistry based on carbon and liquid water. The molecules simply could not maintain necessary structures. But within the range of pressures actually found in Earth's oceans, even the extreme pressures at Challenger Deep, life in some form probably exists everywhere, there is liquid water and any conceivable source of chemical energy to drive metabolism. The sheer existence of life thriving at such physical extremes should absolutely fill us with wonder and profound respect. It tells us unequivocally that life is not fragile in the way we often casually imagine. Life does not require comfortable, pleasant conditions. Life requires only conditions that do not immediately and completely destroy its fundamental biochemistry, and even then, evolution can push those boundaries much further than anyone would have initially thought possible. Every discovery of life in extreme environments, whether in boiling acidic hot springs or frozen Antarctic ice, or crushing deep sea trenches, systematically expands our understanding of where life might potentially exist elsewhere in the universe beyond Earth. If life can genuinely thrive and reproduce at the bottom of the Mariana Trench, under conditions that seem utterly incompatible with biology, might life also exist in the suspected subsurface oceans of Europa or Enceladus, Jupiter and Saturn's ice-covered moons, where liquid water exists under miles of solid ice, under extreme conditions we once confidently would have dismissed as sterile? The intensive study of deep-sea life under pressure is therefore not merely marine biology or oceanography for its own sake. It is fundamentally a window into the ultimate possibilities and limits of life itself throughout the cosmos. Let us turn now to examine in much greater detail exactly what pressure does at the molecular and chemical level, because understanding these mechanisms reveals why pressure is so challenging for life, and how organisms have evolved such sophisticated solutions. When we compress matter by increasing external pressure, we are fundamentally forcing atoms and molecules closer together than they naturally prefer to, be at lower pressure. Every substance has what chemists call an equilibrium state at any given temperature and pressure, a configuration where attractive and repulsive forces between molecules balance perfectly. Increase the pressure, and you shift that equilibrium, forcing molecules into new configurations. For chemical reactions, this has profound implications. Most chemical reactions involve some change in volume between the reactants, the starting materials, and the products, the ending materials. If a reaction produces products that occupy less total volume than the reactant started with, increasing pressure will favour that reaction, pushing the equilibrium toward products according to Le Chatelier's principle. The reaction essentially runs faster or more completely because the system tries to minimise volume under high pressure. Conversely, if a reaction requires expansion, if the products occupy more volume than the reactants, high pressure will inhibit that reaction, making it run slower or not at all. This means that deep-sea organisms living under crushing pressure must have biochemistry that is either volume neutral or volume reducing in its reactions. Any essential metabolic pathway that requires expansion would simply not work at depth. Enzyme function presents particular challenges under pressure. Enzymes are biological catalysts, proteins that speed up specific chemical reactions by factors of millions or billions compared to the uncatalyzed rate. They work by binding to their substrate molecules, the chemicals they act on, and lowering the activation energy barrier for the reaction. But enzyme function depends critically on the enzyme maintaining a very specific three-dimensional shape. The active site where the substrate binds must have exactly the right geometry, the right arrangement of chemical groups for catalysis to occur. Pressure can deform this delicate structure. As pressure increases, it can push amino acids in the protein closer together, altering bond angles and distances. The active site geometry changes. The enzyme may bind its substrate more weakly, or it may not catalyze the reaction as efficiently, or it may stop working entirely if the deformation is severe enough. Deep-sea organisms have evolved pressure-adapted enzyme variants with amino acid sequences slightly different from their shallow water relatives. These sequence differences create protein structures that maintain proper active site geometry, even under enormous pressure. Some deep-sea fish enzymes actually work better at high pressure than at low pressure, having traded away some efficiency at surface conditions to gain stability at depth. This is evolutionary optimization for a specific physical environment. Cell membranes face their own pressure challenges. Membranes are made primarily of lipids, fatty molecules arranged in a double layer called a bilayer. At normal surface pressure and body temperature, this lipid bilayer is in a fluid state, meaning the individual lipid molecules can move around within the layer, sliding past each other. This fluidity is essential for membrane function. Proteins embedded in the membrane need to move and change position. Molecules need to cross the membrane through protein channels. But pressure tends to order lipids, forcing them into more rigid crystalline arrangements, like a liquid freezing into a solid. High pressure can cause membranes to undergo what is called a phase transition from fluid to gel state. A gel state membrane is too rigid to function properly. Proteins cannot move through it. Transport across the membrane slows dramatically or stops. The cell cannot maintain its internal environment and dies. Deep-sea organisms solve this problem through specialized membrane lipid compositions. They use lipids with more unsaturated fatty acids with double bonds that create kinks in the molecular structure. These kinked lipids pack together less efficiently, remaining fluid even under high pressure. Some deep-sea bacteria produce unique lipids not found in surface organisms. Molecular structures specifically evolve to maintain membrane fluidity under crushing pressure. The chemical creativity of evolution solving physical problems at the molecular level is genuinely astounding when examined in detail. Pressure also affects the hydrogen bonding networks that stabilize protein structure. Proteins are long chains of amino acids that fold into complex three-dimensional shapes, held together by various weak chemical interactions. Hydrogen bonds between different parts of the protein chain are crucial for maintaining the folded structure. Pressure can distort these hydrogen bonding patterns, weakening some bonds while creating inappropriate new bonds elsewhere, causing the protein to partly unfold or misfold. This is precisely where TMAO and other osmolytes become essential. TMAO preferentially interacts with the protein backbone, the main chain of amino acids, stabilizing it against pressure-induced unfolding. Meanwhile, TMAO is excluded from interacting with hydrophobic amino acid side chains, those parts of the protein that naturally avoid water. This exclusion creates what chemists call an osmotic stress that actually helps drive the protein toward its properly folded compact state. TMAO essentially pushes the protein into staying folded even when pressure tries to unfold it. Other osmolytes work through different mechanisms. Some, like certain amino acids and sugars, preferentially hydrate the protein surface, creating a protective water shell. Others interact directly with specific amino acids to stabilize particular structural features. Deep-sea organisms often use combinations of multiple osmolytes working synergistically to provide broader protection across different proteins and cellular structures. The study of pressure effects on biochemistry has applications far beyond marine biology. Pharmaceutical companies use high pressure to study protein folding and misfolding, processes central to diseases like Alzheimer's and Parkinson's where proteins misfold and aggregate. Food scientists use high pressure to sterilize and preserve foods without heat, exploiting pressure's ability to denature bacterial proteins and enzymes while preserving flavor and nutrition. Materials scientists study pressure effects on polymers and other materials. The fundamental physics and chemistry of pressure are universal, whether we're examining deep-sea fish or developing new industrial processes. Understanding how nature has solved pressure challenges through evolution gives us insights we can apply to human technology and medicine. Now let us examine the history and evolution of how humans learned to measure and understand deep-sea pressure, a story of ingenuity and gradual progress over centuries. For most of human history, the deep ocean was completely inaccessible and its physical properties purely speculative. Ancient peoples knew that diving even a few meters felt different, that your ears hurt and breathing became harder, but they had no conception of the true pressures that exist at great depth, because no human could reach such depths and survive. The first systematic measurements of water pressure came in the 17th century, when scientists began studying fluid mechanics seriously. Blaise Pascal, whom we have mentioned before, conducted experiments showing that pressure in a fluid increases with depth. He filled tall tubes with water and demonstrated that pressure at the bottom depends only on the height of the water column, not on the shape of the container. This was revolutionary because it contradicted common intuition. Whether you had a wide barrel or a narrow tube, the pressure at a given depth was identical. Evangelista Torricelli, working slightly earlier, invented the mercury barometer to measure atmospheric pressure, creating the first practical pressure measuring instrument. These early instruments were crude by modern standards, but represented huge advances in understanding. The 19th century brought the first serious attempts to explore the deep ocean and measure conditions there. The British Royal Navy's HMS Challenger expedition from 1872 to 1876 was the first major oceanographic research expedition. They lowered weighted cables to measure ocean depth, discovering trenches thousands of meters deep. They brought up water samples from depth in sealed containers and measured their temperature. They dredged the bottom and discovered abundant life in the deep sea, shocking the scientific world which had believed the deep ocean was lifeless. But measuring pressure directly at depth was extraordinarily difficult. Early pressure gauges could not withstand the crushing forces and would be destroyed. Ingenious solutions were developed. One method used tubes filled with coloured liquid sealed at the top. As the tube descended, pressure would force the liquid upward, compressing the air pocket at the top. By measuring how far the liquid rose, scientists could calculate the pressure. These early measurements confirmed that pressure increased linearly with depth, just as theory predicted. By the early 20th century, precision mechanical pressure gauges had been developed that could survive deep-sea deployment. These used thick-walled metal housings containing mechanisms where pressure deflected a spring or diaphragm, with the deflection mechanically coupled to a recording needle that scratched a trace on smoked paper or glass. The gauge was sealed in protective housing, lowered to depth, and recovered. Scientists could then read the maximum pressure from the recorded trace. This allowed systematic mapping of ocean depths and pressures. During World War II, military interest in submarine warfare and undersea acoustics drove major advances in pressure measurement technology. Sonar systems needed to account for how pressure affected sound propagation. Submarine designers needed precise pressure data to calculate hull strength requirements. Electronic pressure transducers were developed that converted pressure to electrical signals, allowing real-time measurement and recording. These transducers used piezoelectric crystals that generate voltage when compressed, or strain gauges whose electrical resistance changes under pressure. Modern oceanographic instruments use sophisticated electronic pressure sensors accurate to within fractions of a percent. They can record pressure thousands of times per second, capturing rapid fluctuations. Some sensors can function at full ocean depth, nearly 11,000 meters, measuring pressures exceeding 1,100 atmospheres with high precision. An interesting application of pressure measurement is in determining ocean depth from submersibles. Since pressure increases so predictably with depth, measuring pressure tells you exactly how deep you are. Submersibles use precision pressure sensors as depth gauges, often more accurate than acoustic depth sounders. The relationship is simple. Every 10 meters of depth adds approximately 1 atmosphere of pressure. Modern digital pressure sensors display depth directly, calculating it from pressure readings using density corrections for local water temperature and salinity. This allows pilots to know their depth to within a meter or two, even in the middle of the ocean, with no visual references. For deep diving submersibles, pressure measurement is also a critical safety parameter. If pressure readings indicate the vehicle is descending faster than intended, or approaching its depth rating, automatic systems can drop ballast to halt descent. Pressure sensors provide redundant depth information independent of other navigation systems, a crucial backup if electronics fail. The humble pressure sensor has become one of the most important instruments in ocean exploration, enabling safe navigation and scientific measurement in the crushing depths. Let us examine more closely the remarkable diversity of deep-sea creatures beyond the snailfish we discussed earlier, because the variety of adaptations to pressure is truly astounding. Consider the anglerfish, those bizarre predators with bioluminescent lures dangling in front of their mouths. Many anglerfish species live at depths of 1,000 to 3,000 meters, where pressure ranges from 100 to 300 atmospheres. Female anglerfish can grow quite large, up to a meter long in some species, while males are tiny, sometimes just a few centimeters. The males parasitically attach to females, fusing their bodies together and living as permanent parasites, an extraordinary reproductive strategy. These fish have soft gelatinous bodies with minimal bone structure, reducing the mechanical stress from pressure. Their muscles are relatively weak because in the still deep waters, they can drift more than actively swim, conserving energy in an environment where food is scarce. The bioluminescent lure contains symbiotic bacteria that produce light through chemical reactions, attracting curious prey close enough to be engulfed in the anglerfish's enormous mouth. Then we have the bizarre barrel-eye fish, whose eyes are enclosed in a transparent fluid-filled dome on top of its head. These fish live at depths around 600 to 800 meters. The transparent dome allows the tubular eyes to look upward through the fish's own skull, detecting the faint silhouettes of prey above against the dim, downwelling light. The eyes can rotate to look forward when needed. The fluid inside the dome is presumably at ambient pressure, equalizing pressure on the delicate eye structures. This is a beautiful example of specialized anatomy enabling a unique hunting strategy adapted to the low-light deep-sea environment. Giant isopods are another marvel of deep-sea life. These are crustaceans related to pillbugs or roly-polies that you might find in your garden, except they grow to enormous sizes, up to 40 centimeters long, larger than a football. They live on the deep sea floor between 200 and 2,000 meters depth, scavenging on whatever food falls from above, including dead whales and fish. Their large size might be an example of deep-sea gigantism, a poorly understood phenomenon where deep-sea species grow larger than related shallow water species. One hypothesis is that larger body size is advantageous in the food-poor deep sea because it allows for slower metabolism and longer periods between meals. Giant isopods can survive for months or even years without eating, living off stored reserves. Their hard exoskeleton must withstand pressure, but being filled with tissue at ambient pressure rather than gas-filled, they experience no differential and thus no crushing force. The Dumbo octopus, named for its ear-like fins that resemble Disney's Dumbo elephant, lives at depths of 3,000 to 7,000 meters, making it the deepest living octopus known. These small octopuses, typically 20 to 30 centimeters long, hover above the seafloor flapping their fins, searching for prey in the sediment. Unlike most octopuses which lay eggs and then die, some evidence suggests Dumbo octopuses may have a different reproductive strategy adapted to the deep sea, though details remain uncertain due to the difficulty of observing them. Their soft gelatinous bodies are perfectly suited to high-pressure environments, containing no rigid structures or gas spaces that would cause problems. Grenadiers or rat-tails are among the most abundant fish on the abyssal plains, living at depths of 2,000 to 6,000 meters. They have large heads and eyes and long tapering tails, hence the name rat-tail. They feed on small invertebrates and organic debris on the seafloor. Grenadiers are important because they are among the fish most intensively studied for pressure adaptations. Much of our knowledge about TMAO comes from measuring concentrations in grenadier tissues. Different grenadier species live at different depths, providing natural experiments in pressure adaptation. Deeper-dwelling species consistently have higher TMAO levels, providing strong evidence for its protective role. Amphipods deserve special mention because they are found at all ocean depths, including the very deepest trenches. These shrimp-like crustaceans are extraordinarily successful in the deep sea. In the Hadal zone below 6,000 meters, amphipods often dominate the fauna, sometimes being the only macroscopic animals found. They are scavengers, feeding on sinking organic matter and dead animals. Baited traps lowered to Challenger Deep routinely capture hundreds of amphipods, demonstrating there is an active ecosystem even at nearly 11,000 meters. Some Hadal amphipods grow to unusually large sizes, exceeding 10 centimeters, another example of deep-sea gigantism. Their success across such a huge pressure range suggests they have particularly effective pressure adaptation mechanisms, though these remain incompletely understood. The discovery of hydrothermal vent communities in the late 1970s revealed an entirely different deep-sea ecosystem, not dependent on sunlight. Vents occur where seawater seeps into cracks in the seafloor, is heated by underlying magma, and jets back out as superheated mineral-rich fluid. These vents support dense communities of specialized organisms including giant tube worms up to 2 meters long, huge clams, eyeless shrimp, and unique fish species. The organisms use chemosynthetic bacteria as their base of the food web, rather than photosynthetic plants. The bacteria derive energy from chemical reactions involving hydrogen sulfide and other chemicals in the vent fluids. These vent communities live at depths of 2,000 to 4,000 meters typically, experiencing pressures of 200 to 400 atmospheres. They face not only pressure challenges but also temperature extremes, toxic chemicals, and complete darkness. The specialized adaptations required are numerous and complex, making vent organisms among the most biochemically unique creatures known. Each of these creatures represents millions of years of evolutionary refinement, natural selection sculpting biology to function under crushing pressure. The diversity of solutions from TMAO production to gelatinous bodies to specialized lipids to unique reproductive strategies demonstrates that there is no single path to deep-sea adaptation, but rather many possible solutions. Evolution is an optimization process, and for any given environmental challenge, multiple solutions can work. The deep sea is a vast living laboratory, demonstrating this principle across thousands of species. Looking toward the future, Technology continues to advance our ability to explore and understand the deep ocean and the role of pressure in shaping its environment. New materials are being developed specifically for deep-sea applications. Carbon nanotubes and graphene, while still experimental and not yet ready for full-scale deployment, offer potentially revolutionary strength-to-weight ratios that could enable lighter submersibles capable of reaching greater depths or staying submerged longer. These materials are hundreds of times stronger than steel by weight, but also incredibly thin and flexible, posing engineering challenges in how to incorporate them into practical pressure hull designs. Ceramic composites combining different ceramic materials in layered or fiber-reinforced structures can withstand extreme pressure and thermal stress, and are being actively tested for use in hull materials and viewport housings. Advanced metallurgy produces new titanium alloys even stronger and more corrosion-resistant than those used in current submersibles, though at higher cost. Some researchers are exploring biomimetic approaches, studying how deep-sea creatures manage pressure at the biological level and trying to copy or adapt those strategies for engineering designs. Could we create flexible, submersible hulls that collapse controllably under pressure like whale lungs do, maintaining internal atmospheric pressure in a rigid inner sphere while allowing an outer flexible hull to compress, reducing the pressure differential that the inner hull must resist? Could synthetic osmolytes or similar pressure-protective chemicals be used to protect pressure-sensitive electronics the way TMAO protects proteins in fish, allowing more compact and less heavily armoured electronic components? These ideas remain speculative but represent the kind of creative thinking needed to make major advances in deep-sea exploration technology. Autonomous underwater vehicles, usually called AUVs, are becoming increasingly sophisticated and capable, and may eventually replace most manned deep-sea exploration, except for special circumstances. AUVs can be made smaller and lighter than manned submersibles because they do not need complex life support systems, pressurized crew compartments or viewports, all of which add enormous weight and complexity. They can stay underwater for days or even weeks on a single battery charge or fuel cell supply, systematically mapping vast areas of seafloor that would be impossible for manned vehicles to cover. Some AUVs can already dive to full ocean depth, reaching Challenger deep and even deeper if such depths existed. As artificial intelligence and robotic manipulation improve steadily, AUVs will become progressively more capable of complex autonomous tasks like identifying interesting features, collecting rock and sediment samples, capturing organisms with robotic arms, conducting complex surveys and experiments, all without direct human control. The trade-off is loss of human judgment and intuition, and the flexibility to respond creatively to unexpected discoveries or changing conditions. A human scientist in a submersible can see something unusual and immediately decide to investigate it more closely, change the dive plan on the fly, spend extra time on an intriguing feature. An AUV following a programmed mission plan lacks that flexibility, though advanced AI may eventually provide some capability for autonomous decision-making about what is scientifically interesting. But for systematic mapping, photographic surveys, routine sampling, and other predictable tasks, AUVs are increasingly the tool of choice due to their lower cost and greater endurance and safety. Hybrid remotely operated vehicles, a relatively new category sometimes called HROVs or hybrid ROVs, attempt to combine advantages of both traditional ROVs and AUVs. These are unmanned vehicles like traditional ROVs, avoiding the life support complexities of manned submersibles, but they are untethered from the surface support ship, instead carrying batteries and operating autonomously, like AUVs most of the time, while still allowing remote human control when needed through acoustic communication links. This gives operational flexibility without the cable tether that limits traditional ROV depth, range, and maneuverability. The cable on traditional ROVs provides power and high bandwidth communication, but becomes a serious liability at great depth, requiring heavy winches and long deployment times, and being vulnerable to snagging on seafloor features. Hybrid ROVs solve this by operating independently, surfacing occasionally to recharge batteries or download data, but controllable by pilots on the ship through underwater acoustic modems when detailed manipulation or decision-making is needed. Several hybrid ROVs capable of full ocean depth operation are currently under development or in early testing and deployment. The Nereus submersible built by Woods Hole Oceanographic Institution was a pioneering hybrid that reached Challenger deep in 2009, but was unfortunately lost in 2014 apparently imploding at depth due to unknown causes. Despite that setback, the hybrid concept remains promising and represents one cutting edge of deep-sea exploration technology. Sensor technology continues its rapid advance as well, driven both by oceanographic needs and by advances in other fields like medicine and environmental monitoring. New chemical sensors can detect and measure concentrations of dissolved substances including gases, nutrients, metals, and organic compounds in real time at depth. These sensors use various techniques including electrochemistry, optical spectroscopy, and mass spectrometry, miniaturized to fit in pressure housings. The ability to measure chemistry in situ without bringing samples to the surface is revolutionary for understanding deep-sea processes and ecosystems. Genetic sequencing devices small enough to deploy on underwater vehicles are being developed that can extract DNA from water samples and analyze it on site, detecting what species are present without physically capturing organisms, a technique called environmental DNA or eDNA analysis. This allows non-invasive sensors of biodiversity and can detect rare or elusive species that might never be captured by traditional sampling. High-resolution cameras with advanced optics, sensitive low-light sensors, and sophisticated lighting systems can capture stunning images and video of deep-sea life in unprecedented quality and detail. All these sensors must be engineered to withstand enormous pressure, driving continuous innovations in pressure-resistant electronics, battery technology, materials science, and housing design. Each advance in sensor capability opens new scientific possibilities and reveals new aspects of the deep-sea environment we could not observe before. One particularly fascinating area of current research involves studying not just how pressure affects organisms at steady state in their normal environment, but how they respond to rapid pressure changes. What happens physiologically to a deep-sea organism when it is brought quickly to the surface in a net or trap? Many die during ascent or shortly after reaching the surface, but exactly how and why? Some fish experience severe tissue damage as dissolved gases come out of solution when pressure drops rapidly, similar to decompression sickness in divers but occurring in reverse. Deep-sea fish adapted to high pressure may have significant amounts of nitrogen and other gases dissolved in their tissues at equilibrium with the high environmental pressure. When brought rapidly to low surface pressure, these gases come out of solution-forming bubbles in the tissues and blood, potentially causing embolisms, tissue damage, and death. Some organisms have gas-filled swim bladders even in the deep sea, using lipids or other low-density materials in the bladder rather than compressible gas. But organisms that do have gas-filled structures experience catastrophic expansion during rapid ascent as the gas expands following Boyle's law. A swim bladder that occupied 1 cubic centimetre at 300 atmospheres pressure would expand to 300 cubic centimetres if brought to surface pressure, likely rupturing internal organs and killing the animal. Understanding these processes in detail helps marine biologists develop better techniques for bringing deep-sea organisms to the surface alive for study in aquariums or laboratory facilities. Specialized pressure-maintaining aquarium systems have been developed specifically to keep deep-sea organisms at high pressure even when at the surface, allowing scientists to study living specimens that would otherwise die immediately upon capture. These high-pressure aquariums use powerful hydraulic pumps to continuously maintain several hundred atmospheres of pressure inside thick-walled steel or titanium chambers, essentially creating a deep-sea environment in the laboratory. Sensors monitor pressure, temperature, oxygen levels, and other parameters. Cameras allow observation of organism behavior without opening the chamber. Feeding and waste removal happen through special pressure-locked ports. Maintaining these systems is technically challenging and expensive, but gives us unprecedented windows into deep-sea life that would otherwise be completely impossible. Scientists have successfully kept some deep-sea organisms alive for weeks or months in these high-pressure aquaria, observing their behavior, feeding habits, reproduction, response to stimuli, things that cannot be observed in the wild due to the impossibility of spending extended time at depth and the difficulty of illuminating and filming deep-sea organisms in their natural habitat. Every hour of observation in a pressure aquarium yields insights that would require dozens of expensive deep-sea dives to potentially glimpse in the wild. The future of pressure biology research also includes ambitious concepts for deploying semi-permanent underwater laboratories that would remain on the seafloor for extended periods, conducting automated or remotely controlled experiments and observations. Small modular submarine lab units have been proposed that could be deployed from research ships, left on the seafloor for weeks to months, conducting pre-programmed experiments and recording data, then recovered for data download and redeployment. These lab modules would have pressure housings containing sensors, cameras, sampling equipment, and experimental chambers, all controlled by computers and running on battery power or potentially fuel cells. Time-lapse photography could capture slow behaviors and life cycles that unfold over weeks, impossible to observe during brief submersible dives that last only hours. Long-term monitoring at a single site could reveal seasonal changes in deep-sea ecosystems, shifts in community composition, responses to events like earthquakes or underwater volcanic eruptions, food fall events when large animal carcasses sink to the bottom. Genetic studies using automated sampling and DNA extraction could systematically catalogue the microbial and animal diversity at a site over time, potentially discovering new species and revealing the complete biome structure. Some proposals even envision networks of these underwater labs spread across ocean basins, communicating through acoustic modems, creating a global observatory for the deep sea, analogous to weather station networks on land. The deep ocean represents the largest single habitat on Earth when measured by total volume, yet it remains by far the least explored and understood of all environments on our planet. Every expedition to depth discovers new species and reveals new behaviours and finds new unexpected geological features or phenomena. We have explored perhaps 5% of the ocean floor in any detail, perhaps less than 1% at the fine resolution needed to really understand geological and biological processes. The vast abyssal plains, the mid-ocean ridge systems stretching for thousands of kilometres, the trenches, the seamounts, most remain virtually unexplored. Each new discovery raises new questions and reveals gaps in our understanding. How do deep-sea ecosystems function, and what organisms fill what ecological roles? How much biodiversity exists in the deep sea, and how is it distributed? What geological and chemical processes occur at the seafloor, and how do they affect ocean chemistry and climate? How much biomass and productivity exist in the deep ocean, and how does this connect to surface processes? These fundamental questions remain largely unanswered despite decades of research, because the deep sea is so vast and so difficult to access and study that our knowledge remains fragmentary and incomplete. Looking even further ahead, some visionaries propose concepts for human deep-sea habitats, underwater bases where people could live at depth for extended periods. These would face enormous engineering challenges, including maintaining life support, dealing with pressure and the need for airlocks or pressure adaptation, importing all supplies from the surface, ensuring safety and emergency ascent capability, and managing the psychological challenges of confinement in an utterly hostile environment. Saturation diving technology, where divers live in pressurized chambers on ships for weeks at a time and make daily excursions to depth, already proves the concept is possible, though saturation diving is expensive, complex, dangerous, and limited to a few hundred meters depth. Extending this to a permanent or semi-permanent seafloor habitat at greater depths would require major technological advances. But the scientific value of having human researchers able to spend extended time at depth, conducting detailed studies impossible with brief submersible visits or remote vehicles, might justify the investment for critical research sites. The deep sea represents one of Earth's last frontiers, and establishing a permanent human presence there, however small and however challenging, would represent a major milestone in ocean exploration. As we conclude this exploration of pressure in the deep sea, we should marvel at what we have learned and remain humbled by how much we still do not know. Pressure is not simply weight pressing down as we intuitively imagine from our terrestrial existence. It is an omnidirectional force arising from the weight of fluid, but acting equally in all directions at any point. It challenges life not by crushing bodies, but by disrupting biochemistry, by deforming proteins and rigidifying membranes and distorting molecular interactions. Yet life has found ways to cope, to adapt, to thrive even under the most extreme pressures found on Earth. From TMAO protecting proteins to specialized lipids, maintaining membranes to gelatinous bodies, eliminating gas spaces, evolution has crafted countless solutions to the pressure problem. Each solution represents countless generations of trial and error, natural selection slowly refining and optimizing organisms for their environment over deep time. The deep sea stands as testament to life's resilience and adaptability, a reminder that given enough time and selection pressure, life finds a way to exploit virtually every available niche, to colonize every environment where existence is physically possible. And as we develop new technologies to explore these depths more thoroughly and systematically, as we discover new species and new adaptations and new ecosystems we never knew existed, we continuously expand our understanding of what life can do and where it can go. The ocean depths still hold countless mysteries waiting to be uncovered, countless species waiting to be discovered, countless lessons about biology and evolution, and the fundamental nature of life waiting to be learned. The journey of deep-sea exploration has only just begun, and the discoveries awaiting us in the crushing darkness may transform our understanding of life itself in ways we cannot yet predict or even imagine. The story of pressure in the deep sea is ultimately and profoundly a story about adaptation, resilience, ingenuity, and the extraordinary diversity of solutions that evolution produces over deep time. It is a story that systematically challenges our preconceptions and assumptions and dramatically expands our sense of what is possible in biology. It is a powerful reminder that we share this planet with millions of species, each one shaped by different environmental selection pressures, each one adapted to different physical and chemical environments, each one representing a different evolutionary experiment in how to be alive. The deep sea and its remarkable inhabitants are an integral part of this grand tapestry of Earth's biodiversity, no less important and no less wondrous than the more familiar charismatic creatures we encounter in our comfortable daily terrestrial lives. By genuinely understanding deep-sea organisms, by truly appreciating the immense challenges they face and the sophisticated adaptations they have evolved to overcome those challenges, we gain a much deeper and richer understanding of life itself as a phenomenon. We learn that life is not confined to a narrow range of comfortable conditions, but can colonize virtually any environment where liquid water exists and some source of chemical energy is available. We learn that the boundary between possible and impossible for life is much further out than we ever imagined, that biology is far more flexible and creative than our limited terrestrial experience would suggest. Every new deep-sea discovery pushes that boundary further, revealing new adaptations we never anticipated, new solutions to problems we did not know could be solved. This expanding sense of possibility has profound implications not just for understanding Earth, but for the search for life elsewhere in the universe. If life can thrive at the bottom of the Mariana Trench under crushing pressure, in eternal darkness surviving on chemical scraps, why could it not exist in the subsurface oceans of icy moons, in aquifers deep within Mars, in environments throughout the cosmos that we have not yet imagined? And we gain necessary humility about our place in nature through this understanding. We humans, with our fragile air-filled bodies and narrow range of tolerable conditions, are not the measure of all things. We are one species among millions, adapted to one particular set of conditions. The conditions we personally find comfortable and pleasant, the one atmosphere of pressure and 20 degrees Celsius, and abundant oxygen that we prefer. These are not universal standards of what is livable or what constitutes a good environment. Life exists and thrives in places where unprotected humans would die instantly and horribly, flourishing in conditions we would subjectively call hellish or impossible. A Hadal snailfish would die just as quickly at the surface as we would die in the Hadal zone. Neither environment is objectively better or worse. They are simply different, and life has adapted to both. This realization should fill us with profound wonder and deep respect for the diversity of life on this planet and the creative power of evolution acting over vast spans of time to shape organisms for their specific environments through countless small modifications accumulated across millions of generations. The deep sea is genuinely alien in many fundamental ways, as strange and hostile and unfamiliar as another planet entirely might be to us. Yet it is our ocean, an integral, interconnected part of our world, covering the majority of our planet's surface and containing the vast majority of its habitable space by volume. The creatures that live there in the crushing darkness are our distant evolutionary cousins, divergent branches on the same ancient tree of life that eventually produced humanity through billions of years of evolution. We share common ancestors with every living thing in the ocean, whether surface-dwelling dolphins or Hadal zone amphipods. We are all related through descent with modification from the first self-replicating molecules, billions of years ago. Understanding deep-sea life helps us understand ourselves, helps us see our own place in the grand evolutionary story, clarifies our position in the natural world and in the cosmos as one species among countless others, all struggling to survive and reproduce in our respective environments. As we conclude this exploration of pressure in the deep sea, we should marvel at what we have learned and remain humbled by how much we still do not know. Pressure is not simply weight pressing down as we intuitively imagine from our terrestrial existence. It is an omnidirectional force arising from the weight of fluid, but acting equally in all directions at any point. It challenges life not by crushing bodies, but by disrupting biochemistry, by deforming proteins and rigidifying membranes and distorting molecular interactions. Yet life has found ways to cope, to adapt, to thrive even under the most extreme pressures found on Earth. From TMAO protecting proteins to specialized lipids, maintaining membranes to gelatinous bodies, eliminating gas spaces, evolution has crafted countless solutions to the pressure problem. Each solution represents countless generations of trial and error, natural selection slowly refining and optimizing organisms for their environment. The deep sea stands as testament to life's resilience and adaptability, a reminder that given enough time, life finds a way to exploit virtually every available niche, to colonize every environment where existence is physically possible. And as we develop new technologies to explore these depths more thoroughly, as we discover new species and new adaptations and new ecosystems we never knew existed, we continuously expand our understanding of what life can do and where it can go. The ocean depths still hold countless mysteries waiting to be uncovered, countless species waiting to be discovered, countless lessons about biology and evolution waiting to be learned. The journey of deep-sea exploration has only just begun, and the discoveries awaiting us in the crushing darkness may transform our understanding of life itself in ways we cannot yet predict.